All right, I hope everyone's ready for another exciting day of talks and workshops. We've got a good lineup of talks and topics today. I will begin by recognizing that the traditional custodians of the land on which we gather today, the Darug people. We pay our respects to their elders, past, present, and emerging, and extend that respect to all Aboriginal and Torres Strait Islander peoples present here with us today. Our first talk is by David Kaunitz. David is an architect and director of Kaunitz Young Architecture. They're based here in Sydney. They're an award-winning firm. They are passionate about creating socially responsible and culturally sensitive architecture, and have done a lot of work in remote regions and a lot of indigenous projects. A lot of work with Randall, and quite a few of them have won awards, and one in particular, which we will see today, did win an International Architecture Award in 2021. I believe that's one of the case studies, and we really look forward to hearing about that. So over to you, David.
Morning, everyone. Can you hear me well? Yeah, good. Thanks for your time today. Thanks for the early start on a Saturday. I'm impressed so many people are here. I'm going to take you through a quick 25-minute journey. It's a bit echo now. I'm going to take you through a quick 25-minute journey of what we've been up to over the last sort of 20 years. It'll be pretty rapid, but I look forward to talking. I'll be around today, so I look forward to any questions or delving into something more deeply. Before we start, just good to kind of take a moment. I'm going to take on this journey and just, we're going to go to some pretty remarkable places. So I hope you enjoy those. Of course, I'd like to, recognise the First Nations people, any First Nations people here, and the people of the Darug Nation. Kaunitz Young have had the privilege to work on Indigenous countries across the nation, designing with communities to support their continual custodianship, recognising the traditional people, their ongoing connection to land, sky, sea, cultures and communities, harbouring their elders, so honouring their elders and intergenerational leadership. The architecture we design occupies country and becomes a part of it. We feel the weight of this responsibility and are committed to a culturally competent process and outcomes that aim to heal country and support communities, protocols and practices. And the natural materials around Earth, which we're going to talk about today, is an integral part of the humanity that comes with that is so important. But our practice didn't start in the desert. Our practice started here in the Solomon Islands, where I lived for quite a number of years doing post-disaster response and community development. And that's a whole other talk. But there was there was a huge focus on local building, on finding ways to where local people could build, working with local vernacular, changing local vernacular only where it was necessary. There's a younger me right there. And really the philosophy that we developed over that period was maximising the use of local materials, maximising local vernacular, but often we went to places where buildings had fallen down and failed, and so there was a need to bring some other engineering and construction practices, and that's the fusion of that. These stone walls are made from salvaged dead coral stone. When I left the Solomons and moved back to Australia to formally set up the practice with my wife, Go Young, the first major project was here in the desert in Wannon, in the Nundara lands, almost 1,000 kilometres west of Alice Springs. And at that time, we had a deep desire to use local materials, and we wanted to make our own blocks actually for this project. And we really came up against the full difficulty of supply chains and costs and the logistics of doing that. How we did succeed in doing these beautiful stone walls with the stonemason who worked with local youth to collect the stones and make the stone walls. But it took time for us to be able to get to the stage where we could could move to the next level with local materials. Just a bit of an overview of the, I think, 48 now First Nations communities that we are working in. All our work now is with First Nations clients, either through government, mainly through Aboriginal corporations, and other ways directly through community. And most of those places you get to this way, I don't know why I got the idea to build out of earth, but you know, it came to me one day. And then, you know, you fast forward a decade from Wannon, which is that project I just showed you, to this, where we finally got to the point where we were able to convince clients to use rammed earth and use local materials. And in a way, you know, the whole philosophy of designing with country and the budgets for these projects, sort of, and the sophistication of these projects got to a level to allow that to happen, really. It was the easiest conversation I ever had in my life, convincing a client to do rammed earth. We did a lot of preparation. We were, you know, in a lot of angst. This was our moment to finally make it happen, and it took about 5 minutes. And I must thank Luigi, actually, for his building, which came just before this, for Twiggy Forest, that was kind of able to kind of get it across the line. It was hard to argue with that beautiful project. So I'm going to skip through this. There's a lot written about this, and you know, there's a lot written about it, so I won't go into too much. But essentially, this building is clad in rammed earth. It has a cavity. It's a masonry veneer building. It's got a cavity and then an insulated frame structure in the inside. All the earth comes from the site, and it's stabilised with cement, because we do work. You know, these are funded by the Commonwealth Government, and we have certain expectations from them, rightly so. Like all our projects, a really large amount of co-design and co-collaboration, even in this one using augmented reality here with some of the community ladies. It's a simple kind of courtyard building, I suppose, but I say simple, but there aren't many examples of courtyard buildings in Australia. Actually, it's a very unusual archetype, even in desert places. And you know, I think that also took this project to another level. I mean, it works climatically beautifully now. Now the trees have grown and the landscapes grown. In fact, you can't see the building from the street anymore. 3,400 plants have all grown and shaded the building. But the central area, the central waiting, the courtyard serves as kind of the fulcrum of the building and the central waiting and the connection between the admin and the clinic side. This was what the building looked like once the rammed earth went up. Richard from Murchison did these walls, and we had a bit of a delay with the steel work, and this building sat like this for quite a number of months, and community members would drive by and look at it on the way to the shops, on the way to their daily journey. There was a huge excitement. They started naming it after this building in Tatooine in Star Wars, and you know, and I think, you know, what we learned from the stone walls all the way back in Wannon, which was those simple stone walls really made the community feel like country was part of their project, was part of the building, and therefore the building was connected to country. We saw that at a whole other level on this project, and that's subsequently what we've seen on other projects. I'll just skip through these. There's the site works. This courtyard now these trees have now grown, and the opening here is now almost full of tree canopy. A lot of solar on this building. I mean, the sustainability on this building, you know, is a good step forward. I mean, there are practicalities with delivering these buildings and restrictions, but the building, essentially, if they turn the air conditioning off at night, would run 90% on the rooftop solar. So, I mean, it's a very sunny place. It only rains twice a year, so there are some advantages. And then, you know, there's a whole other talk here on the great connection with local artists and community members, and the whole process of connecting the community through art here. So I'm just going to play you a short video. This is part of the post-occupancy evaluation of the project. We organised this video to be made. We didn't go there. We left this in the hands of the community to tell the story of what the building meant to them. And I just think it's important to understand, you know, you're all much more greater experts in rammed earth, I'm sure, than me. But what we're interested with local materials, what we're interested with the rammed earth is the real connection, the humanity of the material, and the way it can elevate buildings and make make them really culturally appropriate in this case, and loved and cherished, and then hopefully looked after.
This song, it's about it's healing and in the ocean. Here. That's where I am now. The same thing what they done to me. So, that's the oak tree.
When Palms decided to expand our primary healthcare remit into Newman from the desert, we really wanted to take the community along. And after appointing David as architect for the project, we decided to actually involve the community in designing what that clinical hub will look like. And so David and I spent quite a lot of time in the desert, driving many nights and driving long distances to just ensure that what is designed is accepted and used by the people. It's one thing to design a building and they do not feel part of it. And so we really wanted to change that to also include the cultural aspect of the local people into that design.
Yeah, I just clearly inside. Like what? What one Bomado got that? You, the good people, I like it. All the matter people that this one. What I don't know. Matter I don't know what I don't know.
All right, on that positive note, I might end the video. There is more to that, which we'll show you another time. But just to move on to another project, this is the Barker Cultural Centre. The photos are a bit sketchy still here because it just finished last week and it hasn't properly opened or been photographed on the next in May. This is in Wilcannia, 1,000 kilometres west of here. It's a cultural centre for the Barkindji people on the Barker River, on the Darling River in Wilcannia. It rehabilitates a destroyed by fire a heritage building that's much loved by the community and uses rammed earth to connect with the existing beautiful stone buildings of Wilcannia, grade 1 listed in some cases. Alex obviously did rammed earth did a superb job here, making these moulds and fulfilling the architect's every whim, no matter how hard it was. And so I'll just take you through this again. This actually was next level consultation in many ways, and I think the design of the building really shows that the design was really handed over to the community. I don't think it's really something we would normally design, and that's Uncle Badger Bates there on the left, sketching out from the first meeting exactly what he thought for the site. But many years actually of engagement with the community. And really at the core of the building, it was about using rammed earth to connect with the local vernacular, local stone buildings to continue the beautiful character of Vulcania, but to do that in a contemporary way and to do that in a way that was fitting of a cultural center, which is quite important to local people. This is the context of Vulcania. The building is arranged in quite an interesting organic form. You have the old heritage building down in the black lines on the two street frontages, and then this undulating form at the back of the building, which was to create space, which was designed to create spaces that replicate the spatial feeling of being on the river. Each bend in the river was inhabited by a different family, had a different place name all the way through the one into the other, and so we're looking to recreate that spatial quality and to create a diversity of spaces for different age groups and different uses. And then at the centre, there's this elliptical keeping space, which originally was meant to be two-storey and go down into the ground to naturally cool the building, but because of the COVID inflation, it got cut, but the ellipse is still there, and there it is, right on cue. So this will be the sacred keeping place of the cultural centre and will allow artefacts to be returned from mainstream museums in the capital cities. There's Marnie with her very proud moment of the most maths she's ever done in her life, designing this doorway. Her parabolic, I had to first teach her what a parabola was, but she... What sort of floor is that? That's a concrete slab floor, yeah. So this, Aysh will talk a bit more about this, but this is single skin rammed earth. So we're grateful for her to get this across the line because it really made all the difference, with this project to really maximise the value of the rammed earth. And it was a very tight budget. It's a $5.5 million project, including all the remediation to the heritage building. So, for what is a relatively complex building, and having a single skin of rammed earth actually really helped maximise the architecture and connection to country and was cost effective because we were using it on both sides effectively. Always some integration of art. This is artwork done by the school market, some work with school kids, and they each did a drawing and then they were put together in some beautiful collages. A lot of work was done by Alex to do some testing of the colours and to really try to match the existing stone building. So there's the existing stone of the old building and in different lights, and just making sure the mix was right for that. And here are the different sample mixes. So it was a conscious decision of doing that. In fact, I believe the mix came from the same location where the mortar for the old colonial buildings was taken from. So it was a really good colour match there with mortar, the old building. There you go. There's the glamour. That probably is the most interesting slide out of those. And then there's the first panel going up. Interesting just to see. I mean, I know you all know a lot about these things, but just interesting to see how it went up with the fluting and how the moulding works and the tapering at the top, which was no end of problems. But exists on all our projects. It looks good. So. And there's inside, just you know this of course, but the beautiful quality it's created, and the community is just so happy with the building, how it reconciles contemporary and historical and fuses the two things together and still honours the old heritage building, which is really quite loved by them, and celebrates that. All right, how am I doing for time? Good? 10 minutes? Yeah. Okay, good. So I'm just going to skip through some current projects. This is a project in Waimikata in Port Augusta. It is a 32 plus palliative care, so 34 bed First Nations aged care, residential aged care facility, including high care, built in the valley of two sand dunes. So let's see there, and the total, it's quite a large rammed earth building. It's 2,000, about almost 2,400 square meters, elevational square meters of rammed earth. All the rammed earth is structural, and you'll see that in the coming slides. And Alex and Richard are out there as we speak, or they better be out there as we speak, building. There's a sense of the scale of this project. I think when everyone arrived on site, everyone took a breath to just the scale of what had to be done. And you know, given the location, not too remote near Port Augusta, but still the site, this definitely has its challenges, although no trees to worry about. And then here's some of the work that's been going on. You'll no doubt have lots of questions about this or understand this much better than me, but you know, everything's slab on ground. You know, the starter bars coming out of the slabs, and then the rammed earth being built with Rio inside, and the steel work was still connecting to the top of the rammed earth. Some of the material. Richard assures me this is like the best quality dirt he's seen. So lots of shards, he said. So I take his word for it. So I heard some of you did some rammed earth yesterday, but we have a team. We always have young architects who have not experienced these kind of things. So we have 2 young architects working on this project, 2 great young architects, and they spent a week out on site, working out of the site shed, and got their chance. Here's Anastasia's chance. Last time I showed this video, I got in trouble for health and safety, showing this for health and safety reasons. So please don't share too widely. This is Anastasia with her chance. So, I mean, it's important, right, to give everyone in our office an appreciation of what it is to build. It's not an easy job, and especially when we design such huge buildings out of it, and expect, such good quality. So, it's good for them to know that. And this is actually this week's photos. So the steel framing is going on the rooms. You can see still inside, we've got some stud work walls around the bathrooms, the timber stud work walls. There's steel, but most of the structure is timber, actually. The secondary structure is all timber. Just 2 last projects. This is Kau Takajara, which is sort of 200 kilometres west of Uluru, on the WA-NT border. It's 20 kilometres from the border. Here we're also designing a version of Wami Kata, but this is obviously seriously remote. This is sort of 750 kilometres west of Alice Springs, and not like Wami Kata. It's very remote. This has just started construction, but it started construction. I was just there this week. It started construction in the yard in Alice Springs. It's going to be 58. They're called 54 of the 58 slabs. It's going to be 58 prefabricated modules on post-tension slabs, which is a system we've used a lot in our desert projects, and all steel frame. In parallel to this, they've started doing the foundations to build the rammed earth on site. And so these modules will plug in and be wrapped in to various degrees in rammed earth. So there's kind of a high degree of integration, trying to get this building not to look like a mining camp, even though it's prefabricated, to get it look like it's really well connected to country and a humane place. After all, residents, there'll be residents there, their home. Here you can see on the edge here, there's a bit of a flange, that we built out on the edge here. Rammed earth is actually going to be, the earth is going to be rammed on this slab once it gets to site at the entry to every resident room. So the rammed earth will wrap around here, curves in, and forms an entry feature. So every time the resident goes in their room, they're sort of walking towards rammed earth, and they sleep out on the veranda quite a lot. So they'll be sleeping against the rammed earth. So I don't know if anyone's rammed earth on prefabricated slabs, but if you have, I'd be appreciated to hear how it went before we did it. But anyway, it's going to happen. And of course, there's some complexity that we have to allow for part of the roof to be taken off so they can get into ram the earth. There's all sorts of conversations about ramming up against, we've effectively got permanent formwork, so ramming up against the wall and the waterproofing issues of that, although we are in a very, very dry location. So there's been all sorts of complexity around. With this system, unfortunately, you're also very hard to get set downs on the edges because it's a kind of, you can see the edge of the slab. It's kind of a waffle. It's not quite a waffle slab, but the edge beam, which is quite big, is set in, and there's a sort of a flange that sticks out around the edge of the slab. So it's very hard to get set downs on the edge for waterproofing. So there is a bit of complexity there around waterproofing, but we think we've got that right. And then I might just finish penultimate slide on a project which you can maybe ask some questions about. This is just about to start construction in Ballina, and it's a 3-story Aboriginal Health Service clinic. This came under all sorts of pressure from the budget, this design, and at every stage the First Nations board defended this design, defended the rammed earth, stopped us from taking rammed earth out to save costs. They were, it just goes to show how beautiful the materials, how humane it is. I think in this case also, they really understand the sustainability benefits and the embodied energy attributes of it. They really valued that as well as custodians. I think that's, you'll see more about this probably towards the end of the year and next year. So I might just finish my talk there with one last quick video from Eden. Eden is a artist from the Biripi Nation. She wrote this beautiful poem for the opening of this clinic, which I didn't show today. It didn't have rammed earth in it, but it really does go to the impact the work has in community and to individuals when care is taken and when people are involved, and the importance of that and the importance of the humanity of the whole process, of the materials and the design of everyone who works on the project and everything that goes into it.
Small building. Just one small building was all they asked to do our job well and complete our task. Just one small building to treat us all, to look after our health and be on call. 2 angels working side by side, reading and Auntie Pat with love and pride, giving vitamins and band-aids and booster shots of B to keep us all strong and buildings free. Just one small building, it was the start for the doctors to come and check our hearts. And from the beginning, my mother would clean, scrubbing and polishing till everything clean. Just one small building, and then there was 2, with Dr. Fisher inside, waiting for you. Yes, just one small building, and just look how it's grown. A building we are all proud of.
Thank you.
We're just on time.
Okay.
But if we do have a panel session at the end, like we did yesterday. So all your questions, or if you're really burning to ask something now, then maybe we can allow another minute if anyone has questions for David. Oh, you got a question?
Just a bit of interest. It sounds like you started with doing rammed earth almost like as a skin on the outside. Are you now sort of moving to use that as more of a single skin wall? It was hard to tell on some of those later buildings.
I think we're still exploring. It's kind of horses for courses. I mean, we would like to use rammed earth structurally just from an embodied energy perspective, and to but then more structural work has to go into the rammed earth, right? So.
Just looking at it from like a health point of view, particularly since a lot of these are healthcare buildings, isn't it, the indoor air quality and that sort of help about having that as an inside rather than just as a look from the outside.
Yeah, so I mean that's
considered.
well, with health buildings it's more difficult because with health buildings we have so much going on inside the rooms, and we have the need for clinical services and other things going on, I'm sure you're aware. Where we're doing a single skin, it's in cultural buildings, not in health. We haven't done one in health buildings. The new health buildings that weren't in this presentation, they will expose the rammed earth in waiting rooms and those kind of rooms. The clinical rooms still remain sort of, fully blind and hygiene.
One of those shots before it had an internal wall that looked like a stone building. Was that a rammed earth building with stone on the face, or was that a full stone?
That's the old heritage buildings. That's the remnants of the old heritage
That's the
building,
remnants.
colonial building. Yeah, so that was there.
You mentioned about business reports with that situation of Hawkesbury. Maybe you should get a bit more education so you can push harder to keep the cement out. I think that doesn't do much for the cause by having the cement, which causes other problems, makes the earth building without it look bad.
Yeah, so
Push harder.
yeah. Well, I think the thing to appreciate. I mean, I get it. I mean, we would like cement, obviously. Like we like that. The thing to appreciate is that on all those projects, we are architect, lead consultant, contract administrator. We have a contract with Commonwealth which says if anything goes wrong at any time, in any continuum space, in any parallel universe, we are responsible. So the liability we carry on these projects is enormous. It's enormous. And to even go to Randa in the first instance was a huge risk. But you're right, and where we are, the world has moved and things have moved on since we first did it, and we are looking at carry out. The worst thing for us would be to have a failure on one of these buildings. Because if we had a failure on one of these buildings, then at the moment, all our clients want to do Randa, right? And government is fully supportive. And in fact, in Wilcannia, the budget, because of COVID inflation, the rammed earth was at risk, and the federal government stepped in to say, no, you can't take the rammed earth out because it's so important in the country, right? So the worst thing for us would be to have a failure and to undermine that capital. I completely agree with you. We will get there, and I look forward to some advice if we can get it. Yeah. Well, Alex seemed to like cement in the round.
Yeah.
Are the local people now considering building in Randburg for their own dwellings or for other dwellings? What's it called on?
Well, we don't do any residential work really.
No, but do you see some movement towards them having their own Randburg, doing their own thing?
Oh, the community.
Yes.
Oh, I see. So we are doing a project in Weemole, which is in Arnhem Land, for the range up there, and that project we are training local people how, but we're not, which local people are being trained to build the brand earth construction there. So it's a series of staff accommodation and ranges. It's kind of like Thunderbirds in the bush. But they are doing that. I mean, there's a lot of complex, like it's hard to do training in remote communities, and that's not on them, that's on us. That's on us that we find it hard. And the problem with these projects, they're so big and immense, and the timeframes are so short. What we need is a slow drip project that allows the training to happen, and that's what's happening with the ranger space. They're building 1 or 2 staff houses, which are very modest. They're kind of like almost flats, really, like they're individual buildings. They're not like a full-on house. And the buildings, it's a whole campus that will slowly get built over time. And that's the condition we need to allow that training to happen. You can't do 2,400 square meters of plumbing cutter in 4 months or 5 months or whatever. We've given them, and easily train local people.
When you talked about, I think, the Ballina project, was it cost restraint in the trying to remove the rammed earth, but then local people said, no, that was part of their culture. So the cost reason for trying to remove it.
You know, we've all been struggling with inflation over COVID. A lot of these projects were funded before COVID, so they were in a different paradigm. And so when it came to the point where the project can't go forward, we have to do something to make it go forward. Everything was on the table. I mean, we don't want to take the round earth out. We're the last people who want to take the round earth out. But everything was on the table, and I mean, it's a choice between having a clinical community or not. Then everything has to be on the table. But it's yes, but the reaction was very firmly from the client, the First Nations client, the Aboriginal Corporation, not to take that route. But that was extreme. But we did reduce it a bit, and sort of augmented it, but still a lot of round earth projects.
The air conditioning or the conditioning of the buildings in the remote desert communities, are they swampies or are they?
No.
They're not open sort of buildings with all air thrust.
No.
Never considered that.
Yes. Yes. Mechanical engineers happen. You know, it's again, it's just, you know, like these buildings are showing they're big, like Dr. Wheeler is a big build, you know, it's a sort of $40 million project, and so there are certain expectations put on us by the client and otherwise. So so yes, I mean we would like
It's just healthier in a hospital. It's in a dry climate.
Yes.
Back this.
You're a hard crowd. We don't. Hey, they don't have it's okay. Wow.
I feel bad that we have to cut short this session because there are so many good questions and there's really good interaction. I really don't want to disrupt that, but we do have that Q&A session, so please make use of that. Next, we've got Aysh Venkatesan. Aysh is an EST consultant and building physicist. She's currently the senior associate for Team Catalyst, that's an EST consultancy firm in Sydney. I understand that Aysh and David have worked on a lot of projects together, so that could be an interesting Q&A session later. Aysh specializes in sustainable building design, focusing on low energy and highly thermally comfortable buildings, and she's very proficient with many thermal modeling tools, and for us over here, thermal modeling is a hot topic. So I'm sure there's going to be a lot of questions. I shall be talking about compliance process for earth buildings. So thank you, Aysh.
Thank you.
All right, a bit about myself. I started as an architect. I studied architecture. I'm a trained architect. But somewhere along the line, I did my master's in sustainable design. I met my friend boss, PC Thomas, there, and then he took me under his wing. And it's been a very long journey. So at this point, I sit between architects and engineers, and I'm not quite sure what I am at this point. I'm sort of in between the two. Marrying these two very, very difficult professions. And we've been very grateful that we got to work on many of David's projects, and we've been very happy to contribute to these wonderful projects and communities. And there was a question that was asked, I'm just going impromptu here, as to why, in some places it is single skin, in some places it's just a cladding. So how does it work? It works rammed earth works, rammed earth, sometimes the design works, sometimes the material works. So it is a balance of these two that makes the project work. We can't entirely attribute something to rammed earth. We can't completely say it's only the design that's making it work. It's the balance of these two that actually make the project work. And how do we, go with compliance? How do we make these projects comply? That is a big question. So I think yesterday there was some talk about residential compliance, particularly in New South Wales from EBAA 16. But generally for non-residential buildings, we follow the National Construction Code, and the code is set up into two parts, volume 1, volume 2, there's a volume 3. But for energy efficiency, for compliance with section J, we refer to volume 1 and volume 2. And in volume 1, the code is, is again split into two parts. It either prescribes a set of requirements. It says, okay, you do this, 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 and this. Therefore, you comply. You don't have to prove anything. You just do exactly as I say. It's a tick box exercise. You comply, no problem. Or it gives you a series of verification methods. It says, okay, it is a little bit more involved. There is a little bit more physics involved. There's a little bit more work involved. And if you go through that process, we can help you, or you can prove compliance. The code doesn't help. We have to do the work, but then we can prove compliance. So one of the most commonly used methods for compliance, particularly for non-residential buildings, is what is called as J1V3 verification using a reference building method. So why do we do that? So when we talk about building energy efficiency, right? First thing is, what is the building? What type of building? We saw an aged care facility, we saw a healthcare facility, we see residential buildings. There are many, many types of buildings, there are many types of uses. So how the prescriptive elements for the code is determined by the classification of the building first. So what is your building classification? How do you use it? At what times do you use it? Is it going to be a 24-hour operation, or is it a daytime operation only? So that comes in first to understand how the building is going to interact with the environment. The next part is the thermal fabric. You've got lightweight construction, you've got thermally massive construction. Physics doesn't, distinguish between rammed earth or, brick masonry or concrete. At the end of the day, all these are massive constructions, thermally massive constructions. And then you have the fast response, lightweight constructions, because that's how the equations work. And then you have glazing, the all-important glazing part of it. And then the quality of construction and the air tightness in the building itself. And then around all this is your climate. Where do you build in Australia? That is a huge, huge part of, how we get these buildings to comply. The Devonport one is again climate zone 4. Docker River is also climate zone 4, but two very different responses and two very different problems that we had to overcome, or we have to solve it. So again, there's a huge variation within the Australian climates, which is shown by this map. That's the official ABCB map, the climates. But that's sort of what it seems like, So I always have this map just to give me a guideline. Mentally it brings up this image. Okay, we are dealing with this country because I'm so used to the Eastern Seaboard. I'm a migrant here, so Sydney is quite understandable. But the rest of it, I need to go back to this to get me some understanding of what exactly are we looking at. When we talk about Middle Australia, we're not talking. It's not about climate zone 3 or 4. It is about Saharan desert conditions. That is what we're talking about. But the code only has 8 climate zones. Okay, so they apply this to the whole of the country, and that is quite blunt, to be very honest. It is quite blunt. So they do recognize that it is blunt. So that is why they are allowing us to use these verification methods to prove compliance with the requirements. Okay. Next is what is it in the code? So we are talking about rammed earth walls. So the section that's relevant to us is J1, building fabric and walls and glazing. From 2019, the calculation methodology was changed. Earlier, we were assessing walls separately and then glazing separately. We had a separate glazing calculator. We had a separate wall performance requirement. In 2019, it changed, and it should change. It was a good change in that the code started recognizing that your windows and walls are not two different components. It is the part of the same thermal fabric. You know, it is the same thermal envelope. So you should not actually evaluate it separately. It should be combined together. So what it says is for all, now this is for majority of the climate zones. Okay, so for most of the classes, the U value, the total system U value for the wall and the glazing combined is a U2. So if you convert that back to an R value, it is an R.5. So that is what we get for a 250 mil, uninsulated single skin rammed earth. So if you have a double brick wall, you get R.5. You have 100 mil concrete wall, that's R.5. And for uninsulated rammed earth, it is the same R value. But the complexity comes when you introduce glazing in it. So if no glazing, even the most, high performing passive house glazing, triple glazing, it still doesn't work as well as an uninsulated wall. So when we're talking about passive house glazing, sometimes, with timber and say using a warm and spacer, we are able to get it down to 1.1 in Australia, U1.1. And that is really, really high performing and really, really very expensive. And most of the commercial projects, we don't get to that level of glazing at any point. So when you mix glazing and earth or any masonry wall, it is very difficult to achieve that U2 value. And hence why we move into the verification territory where we have to do something else. We just can't go with a simple DTS solution. And it gets further complicated when we're doing a class 3 or a 9C building, which is aged care, where the requirements are more stringent. It comes down to U1.1 for 1, 3, 4, 6, and 7, pretty much the territories that we work in. And that is because aged care buildings and class 3 buildings are 24-hour operation. You're using the building during the night and during the day. So when the equations completely change when you're using it during that, there's no solar load coming in, and the building switches from heating to cooling mode during that time. So, and that is why you have all these increased redundancies. So what do we do? What does the verification method do? We use building energy modeling, we use simulation, and we build we build a reference building model, and we build a series of proposed building models. A reference building model is nothing but, we take the architect's design, we remove all the nice shading features, because the elemental provisions in the code are derived from an uninsulated building. There are so many variations, so many designs. We can't actually calibrate the code for all these designs. So we have a series of archetypes, and all these archetypes are unshaded, okay? So to sort of mimic that, to comply with that, we remove all the extra shading from the building, and we build the reference building model exactly the way it will comply with the code using your deemed to satisfy provisions. So that is a code compliant building. Now, when you apply all the other specifications, meaning how long should the building work, or meaning what is the internal use, the schedules, for what time is it occupied, what are your thermostat conditions, how much lighting you can have in the building, what are the internal loads, what is the people density, and all these things. You put all these things in the model, and you simulate the model for the whole year, for all the 8,760 hours in a year. You get an energy budget. Now that becomes a target. So that is a very real budget, right? So it is not a checkbox exercise anymore. We get an energy budget. It says, okay, for this building in this location, this is your budget. Now you can go do whatever you want in your proposed building, as long as you keep the same geometry. And if you're under the budget, you pass. If you go over the budget, obviously you don't pass, you have to do something else. So Is it as simple as that? No, there is an extra layer of complexity because the code has come back now and said that it is not enough if you just pass energy, you should also prove comfort. So how do you prove comfort? It is by using a PMV metric. So to be very, in broad terms, what is PMV? This was a metric that was derived by an European who was sitting somewhere in warm Mediterranean climate, who went to an office building where all people wore similar clothes and, where temperature is controlled. And he did a survey in a very homogeneous environment. And he said, okay, how many people feel comfortable in this place? If more than 80% of the people feel comfortable, then you're great. If more than 90% of the people feel comfortable, you're even better. So this is the PMV method. And that's based on, what sort of clothing you wear, what is the air temperature in space, what is the radiant temperature that's coming off your surfaces, what sort of activity you're doing, what sort of airspeed you have, and all these metrics, and the relative humidity in space. So is this PMV method really applicable for buildings that are not offices? They're not. So the next iteration of the code, the 2025 iteration, has recognized this, and we are moving away from the PMV method. But for all of us who are stuck in between, from 2019 to 2025, unfortunately, David's team has had to cope a lot of problems with that, and we had to work around it. We are really stuck because we have to prove compliance. We can't go and argue with a certifier to say the PMV doesn't work because that's not his job. He has to actually go by the requirements of the code. And the ABCB is not going to do anything for us, give an exemption, because they are not actually, they only write the code. Compliance is with the state, so it is not their problem. It's the state's problem. So we really don't have anywhere to go. So we just get very inventive with the physics. We get very inventive with solutions. We really understand building physics, and we know, how each of these buildings react. And that is where using rammed earth in different parts of the building really helps. In some projects, Vamikata, we use rammed earth in the middle. When one of the photos that David showed was, we had 2 residential units, and the dividing wall was actually rammed earth. Because what we found was for that climate zone, for a class 9C, using rammed earth on the outside was not really beneficial, because it's a great material. And earth has to be used on the inside because it's a great stabilizer. It is able to stabilize the environment. And it was really needed there because that temperature had that climate, there was a lot of diurnal going on there. There was a lot of heating and cooling demand. So having the earth in the middle was much more beneficial than having it in the skin. And for the skin, we needed something that was fast response and that, had to satisfy with the code because we have to, at the end of the day, we have to get an OC for the building. So, that's where all these play comes in. Where is it used best and how do you respond to that particular climate? Okay, and going down into the JV3 process itself, what simulation software? So what is this simulation and how do we use it? And can any tool be used to comply? No, you have to use a tool that is ASHRAE ANSI compliant, and it has to undergo a series of testing. And what we use is Energy Plus. It's actually developed by the US Department of Energy. Mr. Trump doesn't know it, and we hope he doesn't, nobody makes him aware of it, because it's a great contribution to the world. The US government has spent, I think at this point, about 600 to 800 millions of dollars. It is free to use for everybody in the world. Every single energy simulation software, which has got a front end, a graphic user interface, is actually running on the US DOE Energy Plus. It's a brilliant piece of software. It's had some 20-25 years of R&D going into it. And that's one of America's greatest contributions to humanity. We just hope nobody tells it to Mr. Trump. So, okay. And we use a front end, but Energy Plus is all computer language. Okay, only I can't do any coding. So we really can't access it that easily. We need a graphic user interface that helps us convert the geometry data that we put in, into the simulation language, and it gives us various results. So we use what's called as design builder, and you can see that we have one single model there, and we are able to get all these outcomes from outputs from that one single model. We are able to do so many analysis, and that is what helps us consult with our clients to help them navigate this very, very complex compliance process, particularly for complex buildings and high-performing buildings. So the most often used ones are dynamic simulation. We do annual energy prediction. We do HVAC modeling. We can do daylighting. We can do life cycle cost analysis. We can do a lot of parametric runs. We are able to do analyze solar geometry, and we can also do some CFD modeling and the stuff. So just to make it a little bit more relatable, not commercial building level. This is the some daylight factor outcomes from a residential building. It was a renovation that we did. And as you can see, it tells you at that one point in time, at a single point in time, what happens to the space, what is the quality of daylight. So we can see that, wherever there are windows, you can see these bright, nice red and green spots. No windows, it's all dark. So this is the kitchen area, and you can see there's a big black. One half of the kitchen is getting light, the other half of the kitchen, there is not much light. So we introduced a solar tube there. This is a very, very old semi, about, I think, 80, 90 years old. So the owners were a bit hesitant to break the roof, but then we managed to introduce the solar tube. And now you can see that the spread is much, much better in the kitchen. Again, the model is precise to the extent that we are able to model, what happens to solar geometry. You can see that's the building, and that's a winter morning sunlight. So this is the eastern facade, and you can see the sun patch in the space, winter morning. So this is what we modeled 2 years before we built. And 2 years after, so that's the house which is finished, and you can see the same sun patch in the space. And we are able to, model all sorts of construction data. This is just a regular lightweight wall, and design builder is able to take in all this information. You're able to describe the wall in different layers. And it gives you a full report of all the thermal properties of the walls. And it tells you what is the U value, R value that you have to calculate. So again, lots of physics work. But what is very interesting is the outputs that we can get from these simulation processes. So it's just not about the annual energy at this point. The code wants you to comply with the annual energy requirement. But that's just an output that we have to give the compliance. But before that, we go through a series of steps, and compliance is never about one reference building model and just one final proposed building model and it'll do the job. No. So we would have gone through, I think for each of these projects, we would have gone through at least about 10, 15 iterations. And so the most important thing with compliance, particularly for very complex buildings, is to start working very early on in the piece to understand what is non-negotiable for the architect and what is non-negotiable for compliance. And then bring those two to the table, and everything else can be negotiated in between, because it's energy, it's a zero sum, it's a pie, right? So the size of the pie doesn't change. So how you make the pie is what changes. Where can you take away some and where do you add a little bit is where the secret is. So we do a series of analysis to understand, okay, where is this building struggling? Which rooms are the problem rooms? So you have this big precinct. You'll have probably 2 or 3 blocks, which are the main culprits, which is sort of bringing the whole thing down. The rest will be fine. So you need to go down to that level, each block, each room, to see, okay, what is happening in these rooms? Our energy might comply, but the the people may not be comfortable. So why are they not comfortable? You are able to see that what is it that is making that room not comfortable. It could, for example, it could be a very, very obscure window. You won't even realize that this window is actually a culprit. It could be the only window in the room, but it's just that it's in a spot where it's sitting between two buildings and it's getting a lot of west lighting. You can't not do anything to it. You have to have the window, but that one room can actually increase the budget by a whole lot. So we first need to understand that, okay, this is my problem, and then we need to start working around it. How do you get it to comply? So again, how do we do that? What you see in the bottom is actually the green line in the graph is your site outdoor drive out temperature. This is for Maroubra, okay? And the blue line is actually the radiant temperature. So there's a lot of temperatures speak in physics. The air temperature, as we call it, is what we use to set the thermostat of an air conditioning system. So that's your air temperature. The radiant temperature is what is radiated off each of these surfaces, okay? And the energy simulation software it computes the sum of all this, and then it averages it to one radiant temperature in space. Radiant temperature can't actually be measured with a thermometer, it has to be calculated. But it is it is a radiant temperature which is closer to what we feel. If you think about it, the air temperature could be 24 at this point, the thermostat. But I'm feeling a bit cold. That's because it is a radiant temperature. The surfaces are radiating, so it's probably dragging the air temperature down. I'm feeling 21. The thermostat is showing 24, but I'm feeling 21 on my skin, and that is making me feel cold. In summer, the thermostat is set at 24, but there's so much radiation that's coming off the material that it's, the radiant temperature could be 28 and 29, and you feel very warm. The easiest example is if in summer, if you switch on the air conditioning system, yes, for the time that the air conditioning system is working, you might feel comfortable. The moment you switch it off, you start sweating again. It starts getting very warm again, and that is a function of the radiant temperature. And why we obsess over this is because, radiant temperature is directly a function of the facade. Everything else can be controlled. The facade is designed by the architects. That is a design feature. And radiant temperature is the one that directly contributes to comfort. So if we get the building shell right, we've solved 90% of the problem in the building. The rest can be maintained. It can be, it's a matter of, tweaking the occupancy, the way people behave, the people dress, and all those things. But the primary function of architecture is to get that facade right, to make it comfortable. So you're seeing big spikes in radiant temperature. It's about 40 degrees, midday. And then we model blinds, external blinds on the outside. And then suddenly you can see that, without the blinds, again, the top graph, you'll see this graph here. You're seeing these big spikes on the western window, it's radiated. The moment you put the blinds, it's softer, the curves. So we just wanted to show to students what happens. How do you actually understand simulation and reality? So we can, it's not just theory, it actually works. And then we get all the other outputs from it. We are able to calculate comfort, how many hours are comfortable during the day, comfortable during the night, and for the period, and all those things. Okay. Thermal mass, thermal mass. The most important, with physics, the most important part of thermal mass, it's a beautiful material, but it has to be protected. It's very important to protect your thermal mass. It looks very nice on the outside, but to make it work, to make it useful, you need to protect and shade your thermal mass. It should be operated like a battery. It's a great storage system. Mass charges every day, and then it discharges every day. So when it is hot, it takes in the heat, it stores heat, and then it discharges the heat. So using thermal mass on the inside as your partition walls, as your floor, as ceiling, works brilliantly. And in Bamikara, the reason we were able to get Bamikara across was because the mass was on the inside. It's brilliant. You might not have mass on the outside. Vulcania, no insulation, pretty much it was just single skin mass. So two things. One, the climate worked, and the second thing, mass worked. So it's very difficult to, or it is, you need to find the right balance. You have to combine a lot of other aspects, but sometimes we hit jackpot in certain, climates. So Vulcania was one such climate, very dry. You had good diurnal. The mass, it was just made for it. You just place the mass. That's it. You didn't have to do anything else. It just worked. No problems. Docker River. Docker again, very, very difficult climate to work with. Very difficult place to work with. Lots of issues with, what we can build and what we can't build with. We couldn't use glass first. It had to be steel structures. It is a termite country. So how do you make it work? And then now, we are beginning to see studies where in remote communities, lightweight construction is fast response, actually. So when you open the doors, it cools down much, much quickly than mass. So how do you work with all these things and comfort requirements between the people, people of Eastern Seaboard? The way we perceive comfort is very different to what happens out back. We think 21 to 24 is comfortable, or even 18, 17, 16 at night is comfortable to 24. Out back, you start feeling comfortable only from 25 onwards. 25 and up is comfort. Anything below 25, you need to pull your beanie up. I come from the southern part of India. So when I go back in December, I can see all my relatives having beanies and jackets. And a couple of days later, even I'm almost itching to pull a jacket on. It's not right. It's only 25. I should not be wearing a jacket, but it's just that, you're seeing everybody in a jacket there, and you feel that because it's your body's response. So comfort is very, very subjective. And the code is blunt. It wants you to keep it between 21 and 24. And the code can't, sort of cater to every single solution. That's very difficult to sort of administer for a huge country like ours. And so how do you do it? Yes, you have to do compliance, but you also have to have enough backstops in your process to ensure that even if, even after complying, there's enough space there for people to feel comfortable. Even if they operate the building at 25, 26, 29, you don't sort of burn a lot of energy, and you don't actually, the building should not fail. That's very important. So our experience has been that, for every climate zone, if the simulation is showing that the thermal mass works, then compliance has been easy. If the design is climate appropriate, then compliance has not been a problem, So we can make it work. As with every single Davis projects, we've made it work. There's not a big problem at all. So there may be a few tweaks here and there, but that's very natural. It's not like, I started on this great journey, I have it, but I can't make it comply, I'm going to bin it. It's not like that. We've managed to get every single one over the line, and well over the line. And that is because the design has to be responsive to the climate. If the design is appropriate for that climate, compliance works, even with a tool as blunt as our code. We've not had issues, actually. One of the most, this is a very big concern of ours, particularly with rammed earth, where people go for composite constructions when it's not a sandwich insulated panel, but you have rammed earth skin and a structural wall system inside with insulation. Using it in climate zones 5, 6, even 2, that is, we need to be very careful with the construction system, because we are creating a zone between the frame and the rammed earth skin, which is very moist and which can either be cold or warm, depending on the season. And that is where mold thrives. Okay, because you are having a cavity where drainage may or may not work. And we post-war construction has sort of evolved into these composite constructions where we put materials together that are not supposed to be put together, that don't exist in a happy marriage at all. You know, we have insulation, which is just wicking water, timber, which can retain some water, but not by much. And then we have brick or heavy masonry, which just absorbs water, keeps it for a long time, and then releases it at a time when it might not be, you know, sort of compatible with the other two materials. So what happens is, on warm days, you know, say for example, Brisbane, it rains, your mass is soaking up a lot of water, and then it starts drying. So the drying diffusion can happen either to the outside or to the inside, depending on that particular day, the climatic condition. So if it is diffusing to the inside, all the water vapor is being absorbed by your timber and by the insulation. If there is no building wrap, or if the building wrap is not installed properly, I've seen building wraps where they just do 1, 2, and 3 nails, and then it's flapping. That's about it. So there's no point. You cannot, you can just take off the wrap, you know, because all you need is a small gap. Your power sockets leak moisture to the extent of 8 liters every day, just the power sockets from the house. So that's the amount of leakage that happens. So if you don't wrap the frame and you create that danger zone, that is where mold thrives. So that is, we should be very, very mindful of, you know, these sort of pitfalls when we use mass on the outside, but you have to insulate it because your climate is calling for it. You definitely have to insulate it for climate zones 5, 6, 7, you know, sometimes 2 as well, because we do have heating and a cooling climate, you know, and we have to have insulation to avoid those issues. And it is the other big pitfall is air leakage, leaky buildings. So mass can be beautiful, lightweight can be beautiful too. It doesn't matter. It doesn't matter what type of construction you have. If the building is leaky, it undermines the entire construction. You know, building leakage is a very, very serious problem. And it is a very big problem for climate zone 6, 7, 8, and climate zones 1. So wherever you have extreme heat or extreme cold, the leak sort of, you know, makes it more difficult to feel comfortable. So we did some simulation, you know, we actually modeled and then we tested in a house. So an average Australian home at this point leaks to about 15 times an hour. So this is a very favorite example of mine. You know, if we all live in a balloon, a nice homogeneous balloon, if we live in that balloon, and then we start, okay, now this balloon is very thin. We need to insulate the balloon because, you know, it's hot or cold outside. We want to save energy. We insulate the balloon. And then we need some windows and doors. We start making holes in the balloon. So, and then we start air conditioning the balloon because, you know, we want to be comfortable. So you put insulation, but you also poked holes. And now you're air conditioning the balloon. So the holes are leaking air. You need to keep blowing the balloon to keep its shape. So at this point, an average Aussie house, you know, you have to blow it 15 times an hour to keep its shape. Okay, so your air conditioning systems are designed for just once. So either the air conditioning designer oversizes it massively because he knows you're going to leak 15 times. So he puts a system which is 5 or 6 times more than what you need so that you don't complain. It's nice and cool all the time. You're just air conditioning the world. Or if he right sizes it, you're going to be forever complaining. It's like, oh, this system is not working. I'm always hot or I'm always cold because your balloon is constantly leaking. So this is your heating demand for a leaky house. It is going up to 20,000 kilowatt hours. That is your thermal energy requirement. That is your peak sizing. So it's saying that you need an air conditioning system that is, you know, that's as big as 20 kilowatt capacity. The next run is, okay, we just did 3 air changes. We reduced the 15 to 3. And that's the difference. So from 20,000 watts or 20 kilowatts, your capacity has come down to about 13 kilowatts. Okay. And then we did the run where we introduced the magic heat exchanger, your mechanical ventilation with heat recovery. And it's come down to about 9 kilowatts. So this is not a function. We did not increase or decrease the insulation in the walls. We did not change the glazing. We did not do anything else. This is just air tightness. It comes down to how well you construct your buildings, how well you tape your membranes, how well you protect it from weather, and how well you detailed it to make sure there are no leaks in the joints. And you're able to bring your air conditioning system, from 20 kilowatts all the way to 9 kilowatts. The biggest piece of machinery you can put in a building is the air conditioning, and it is huge. And going forward in this changing climate, no 2 years are the same. From 2007 onwards, year on year, we've seen a change in the climate. Every single year, the weather has changed. We've seen a change in your climate file. So the buildings don't perform. We can't take it for granted that, okay, you do this, she'll be all right. No, it doesn't happen. So, and we are moving, the RCP 8.5 scenario looks more than likely now, and the 2050 weather is a stuff of nightmare. So we won't go there. But it's sort of, what it's saying is that pretty much for most of Australia, we won't have a heating season at all. And that is quite scary because I've got bananas blooming in winter in Sydney at this point, and it is pointing to that trend. Okay, so with these thoughts, I think we'll go for discussion. Yeah.
Can you model a passive low energy building that naturally ventilated, naturally conditioned through ventilation of mass and not have an air conditioner, and give me passive survivability, climate change resilience, fresh air, all those things? Can you model that?
I can model it, but I may not be able to comply with the code. That's I can model it.
Yeah.
I can show you how it will work. I can show you what needs to be done. Absolutely, we can model it.
Can you use adaptive comfort?
Oh, absolutely.
as the-
Yeah, sitting any students,
ignoring
the first
standards.
semester. Yes, absolutely, we can do it. Oh, okay. All right, yeah. Yeah, sorry.
When you're doing this modelling, where do you get the data? Do you have site data that you're using specific to this collected in the lead up to doing a program?
Yes, there are many formats of weather files available. So we use the current weather files. Sometimes we use the future weather files depending on what is it the client wants. So most of Kaunitz's projects, we put them through the current weather for compliance. We also stress test them for future weather. Particularly if the buffer is very small, we don't take the risk. We always stress them and then go back to them and say, look, this might not work. So yes. Yeah.
So with a round earth building, obviously there's breathability
Mhm.
and the moisture content humidity goes out through the wall and it regulates. How does that factor in with this air tightness concept?
So airtight, you build airtight, but air tightness is very different to breathability. Okay. So you have your, your windproof layer, your down jacket. Down jacket is not the right one. You have a windproof. Like it could be airtight, but it's still breathable. Right. So air tightness is very, very different to breathability. Now, if you're using a single skin rammed, there is no problem. The material is hygroscopic. It will allow for moisture diffusion in and out. If it's coming inside your air conditioning system or your natural ventilation cycles, will remove the moisture. No problems. It is when we have this complex composite constructions where these issues come in. Because by the time it takes for rammed earth to diffuse and for it to dry completely, it's created an environment in that cavity, which is enough for mold to start growing. So it is about that time limit, and that is very, we can determine it now. We do have modeling software, we do have Woofy, and we are able to see that these issues happen. So it is not about rammed earth, it's about quantifying everything. Yes, rammed earth will breathe. Your lightweight system will also breathe. Airtight buildings do breathe. I live in a passive house. Okay, so it's very important that it breathes for us. It does breathe. But it is about quantifying it and to be able to confidently say, yes, even if you have this system, you've got everything in place. Your building is airtight. There is no way to diffusion from the inside. So you should be safe. Yeah. Sorry, I'll just go to the back. She asked.
You said the ground airs, if it's inside the house, you work and stuff, and then you said if it is outside, then there might be issues in terms of like how heat is getting transferred. I mean, like the thermal lag of the airs itself that will create that thermal comfort that we're talking about, but like I'm not quite understand if,
Okay.
if like, you know, if that's a rush statement, because it's just like, or at least so because the heat transmit and make the.
Yes, I'll tell you why that happens. So rammed earth to normal days, okay, if your ambient temperature, your outside temperatures in your late 20s, very, very early 30s, no problem. It works beautifully. You know, it goes from 20 to 30 anyway, rammed earth is fine. But when it starts crossing 30 degrees, when it starts going into 35s and 36 and 40s, you know, the first day of your summer heat wave, and that works well. The second day, it survives. Third day, it starts breaking down because the 250 mil or 300 mil rammed earth has reached capacity. You know, it is storing enough heat. Your thermal mass can only store so much heat. You know, after a point, it's like a battery, it's like a jug, you fill it with water. So once you've hit that capacity, it starts releasing the heat. So where does it release the heat? So heat transfer, right? So heat always moves from hotter to colder. So you have 45 degrees outside in a heat wave. Your rammed earth is at full capacity. You're trying to air condition your house, or you're trying to desperately keep yourself cool. You are sort of, you know, coasting at about 25, 26. So 45 to 25, that's a 20-degree differential between outside to inside. Your rammed earth is full. Now, there is no stop, there is no reduction in the radiation you're getting. It's still getting heated up. So it is going to discharge everything back into your space. And that is when it's very difficult to cool. You know, so you start taking a hose, you start hosing the outside of your rammed earth or bricks or concrete or whatever it is to cool it down. So that is why quantifying these concepts are very important. Yes, rammed earth is a great thermal mass. I'm not disputing it. Can rammed earth be used? Yes. If your climate is very benign, if you're living in Coffs Harbour, it's beautiful, brilliant, because you've got Goldilocks climate. You know, anything will work there, rammed earth will work. But you have a heat wave. You know, that is why people run towards lightweight construction, because it's very fast response. One day you have one southerly break, one whatever, you know, some cool change. You open your windows, 20 minutes later, your house is back to normal. Rammed earth will take 2 days to cool down. So that is why shading your earth, shading the rammed earth, making it, you know, you use it very carefully because it's a battery. How you place it is very important. I live in a two-story, yeah?
I just to say with that, one part of that equation, that's one way of looking at it, but really how we run house, we have the windows up at night time and we cool down those rounded walls. So in the daytime, we've got 20 degrees difference between outside and inside. Windows can even be open. And so the rounded work quite differently. And the air conditioning load is nil, whereas in other areas, now the air conditioning load is probably our biggest load.
I'm not disputing yours. Again, that's why I said it depends on the climate. You know, if you have a day and night dial, if you have that, then rammed earth will work. I'm talking about those places where, you know, we are having heat waves in Sydney. I think this February, January, we had days. Yes, we just landed from here. Yeah. I think we had one day, 41 degrees. The night was 28 degrees. Okay, the second day was 35 degrees, the night was 27 degrees. 27 degrees is hot inside the house. Okay, and what do you do? Even if you open the windows, it's hot. You just...
Not some of the climatized.
But it is summer because we are moving into warming climate. You know, I can show you. No. I can show you the weather file. See, I'm all for energy efficiency, but I'm more for thermal comfort because the biggest mantra in our practice has been that, you know, We don't chase behind energy efficiency. If you design your building to be thermally comfortable, if the building is that thermally comfortable, then people will not reach for air conditioning systems. Therefore, you are naturally energy efficient. It's a byproduct. You know, your building has to be healthy, it has to be thermally comfortable. But to do that, you need to understand the climate. And I don't have the slide here, but I think we did this work for ABCB for the 2025 code, and then we showed them the legacy climate files, the comparison between the legacy climate files to what is happening now between 2007 and 21, and the future climate files. You know, earlier we used to have 8 very hot days during a summer period, and conveniently, 3 or 4 of those days will fall on Christmas Day, Boxing Day, New Year for Sydney. Okay, it was very easy. So 3 days out of the 8 days you're done. You just need to spread out for 5 days. Fine, everybody take a break, go for holidays. You're fine. Your building is fine, right? But now the 8 days has become 18 to 20 days in a year, and it is following a series of heat waves. It's not easy. So this year we've had unreasonably large amount of rains. You know, it's been hot, it's been wet, it's been very moist. And it is very nice to talk concepts in isolation. But when you do it for the whole year, when you simulate it, the model actually does physics works. You know, it is doing a calculation for every hour, every 15 minutes of the day, actually, to see the interaction between the outside and the inside. So it is actually reading a very reputable file, and it is giving you the output. So that's why quantifying it is very important. Yours will definitely work. I'm not disputing it, but it depends on the climate. It depends on where you live and, you know, how you make it work. So it may not be applicable to other areas.
But I mean, also you've got the like winter sun coming in and warming up walls, and also things like solar combustion heaters that uses energy that's like bioenergy, not fossil fuel energy. And then looking at the whole idea, well, what's the purpose of the whole thing? Is just to, we don't have air conditioning in our house, for instance. We don't need it. It just performs beautifully. It's open probably at least 50, 60% of the year. And we find that we adapt to the actual temperatures quite well through the year. And in the middle of winter, in the middle of summer, we can have 45-degree temperature outside and we're at 26, maximum temperature ever. And it feels air conditioned when you walk into it. That's just the cool coming from the mass. And after 3 days, that's the highest temperature, 26, it's usually 24 earlier on, because you've got night cooling, louvers that let the air through, a lot of shading. Shading is so important. West particularly, really chop that right back. And east, even morning sun, that's shaded. So the ways we can do things with shading, not necessarily sealing up. The sealing up idea, I'm not so convinced by, because... You
live in a Randolph house, do you? Is yours a Randolph house?
Mudbrick house.
A mudbrick house?
Yeah.
Mudbrick is naturally very airtight. It is breathable, but it's very airtight. Any plastered masonry is actually airtight. You don't need anything else. The only place where it leaks is around the window, installations. That's about it. The window leaks, the joint between the window and the mudbrick leaks, but any masonry by itself, which is plastered, is airtight.
You have that windows.
Yeah, but if you want to, you can close it. On hot days, if it's 45 degrees outside, you don't keep your windows open, you're able to close it. You draw your shutters. So that is what is making it airtight.
Well, because it has a lot of mass in it. So I should have a discussion.
No, I'm not disputing the mass at all. See, I live in a passive house. So I've got a polished concrete slab, just the plain structural slab. And on a sloping side, I've just insulated the edges of the slab. And that is my thermal mass. In winter, the reason why we started off with mud brick, right? We started off with rammed earth, and I even went to hempcrete. My husband got very, very scared. He said, "Can you please build me a house that looks like the neighbors?" I'm not quite sure I'm game for this. Okay, so it was a 5-year discussion process, and he was quite happy to go buy something in forms. And then I had to drag him back and said, "Look, this is a real test for our marriage, so a lot of conversations." And then I took him to Canberra to show him a passive house that looked something similar that he could relate to. And then I said, "Look, it ticks all the boxes for me and maybe for you as well. So why don't we go down this path?" But nevertheless, it's a sloping site and my mass is on my floor. And the reason I went down the passive house route is because my in-laws, they live with us. My father-in-law is 90 plus, mother-in-law is 85, and they're from Chennai, from South India. So for us, anything less than 25, as I said, is very cold. So that is 80% the time in Sydney. And they want to come live with us because children, grandchildren, and all these things. But at the same time, it's really torture for them to live in this country because, you know, constantly they have to battle between having a jacket on and jacket off and having socks. India, we wear dhotis, you know, it's very lightweight. As you said, it's very open. You know, you wear saris, a lot of places for evapotranspiration to occur and everything. So, but this passive house that we've created with mass and the response system has enabled them to be, we don't heat the house in winter. I don't need a heating system. I have a very, very small air conditioning system, a 5 kilowatt air conditioning system for a 380 square meter house, 2-story house. But ground floor, it's single level and concrete slab. My father-in-law is able to walk without shoes. We don't wear shoes inside the house. We walk barefoot. And middle of the winter, he's able to walk barefoot because my slab doesn't drop below 20 degrees. And that's earth coupling with the slab. So I completely understand, you know, how maths works and how physics works. But it's just that where you apply it and it depends on the design. Yeah.
Sort of more interested in the compliance part of the story. We know it works. We know the thermal mass works. But I guess I'm picking up on Peter's question before about how do you get around the compliance requirements of having a passively ventilated house, for example, if you want to go down that route and you don't want to use mechanical cooling, for example.
See, house compliance is a bit of a tricky problem. All of David's projects are commercial, you know, classes 3 to 9, and there's a little bit of leeway in the code to go down that path because it's a little bit easy for us to do. If you are building anywhere outside of New South Wales, again, compliance becomes easy because the other states and territories allow for verification using reference building method, the same method for houses, and we can do something about it. But in New South Wales, you're tied to basics and therefore to NATAS. And NATAS has, that's a full conference by itself, but NATAS temperature set point is between 16 degrees at night and 24 degrees during the day. You're working within that band. And, you know, our very well-designed passive homes will not follow that band. And that is where the situation comes. So for compliance, NATAS assumes every house will be air conditioned. So it does have its own natural ventilation cycle built in. So they do something very funny, and it's just the way it's set up. Okay, so
I don't really understand that.
right. Yeah.
How are we?
Ah, yes. Yeah.
Oliver Biggs on next. Oliver is a civil and environmental engineer. He works for BSc Consulting, and BSc Consulting does structural engineering and performance solutions for natural materials. So over to you.
Beautiful, thank you. So yeah, a little bit of background about me. I studied environmental engineering, which is an interesting degree, but the work kind of funnels you towards mining or contaminated land. And I worked in contaminated land for a bit and didn't really like it. So went back to doing some carpentry with a friend of mine and got right into building and construction. And then I started working with BSc Consulting about 2 to 3 years ago. So yeah, we do residential structural design. We work on lots of natural building projects, and we do performance solutions as well. So we've heard a bit about performance solutions already. That's what I'm going to talk about today. So hopefully the presentation isn't too technical and dry, but I feel, you know, from speaking to people around the conference, it is a topic that people really want to know more about. Who feels like they understand performance solutions and what they are and what's involved? I'll raise a hand. Yeah. So some of you do. So For the people that are on top of it, you'll probably like the second part of my presentation where I go into like what we actually put into our reports. And the first part of the presentation, I'll just talk about the process in general in the NCC. And yeah, we'll look at an actual case study of a project we did using stabilised rammed earth as a partition wall between two townhouses and look at what performance requirements were involved in that report. So just briefly on the NCC, so it's a performance-based code. So what that essentially means is that you can build your project out of any materials using any methods that you want, as long as you can show that it meets the performance requirements in the NCC. So the other option is like a provision based code, and that's where you need to follow, you know, the strict Australian standards and guidelines. So we kind of have both. We've got the provisional code, which is your Australian Building Code Board housing provisions and all of your Australian standards. So you can follow that and you can build according to the standards, and that's all good. Or you can do something alternative, and then you need to get a performance solution to show that you're meeting the performance requirements that are set out in the NCC. So yeah, it's on a 3-year amendment cycle. So 2025 will come into effect this year. We're currently in 2022, and there's free access. So you can just go to the Australian Building Codes Board website and download these documents. These are the 4 kind of relevant documents. And the way to get your head around this stuff is just to actually read these documents. They can be quite confusing at first, the way it's all referenced and the structure of it. But if you read through these documents, you can get a good understanding about this yourself. So there's 3 volumes. Volume 1 is class 2 to 9 buildings, so more your commercial, high-rise residential, that kind of stuff. We'll be focusing on volume 2, which is your residential up to 3 stories, and then your garages and sheds and that kind of thing. And with the volume 2, the NCC, this used to be combined in the 2019, but now they've like separated it. So you've got the housing provisions, and that's all you deem to satisfy provisions for volume 2. So that's like your prescriptive code for housing, and then volume 3 is plumbing. So with any building project, you basically got these 2 avenues to achieve compliance. So you can go through the deemed to satisfy route, which is showing that you're building your house or whatever it is according to the Australian standards or the housing provisions. But if you're doing something alternative, which is, at the moment, all any earth wall construction is, there's no DTS provisions for it. So you need to go down the route of a performance solution. And your performance solutions are assessed on a case-by-case basis. There's different assessment methods that we use to show compliance, and then you need your building certifier or surveyor to assess that and to approve that, and then you get compliance. So just to outline who's gone through the process of getting a performance solution for their project. So a few of you, so you might know, basically there's a few different stages with the performance solution. It's not just one report. So we start off writing a performance-based design brief. So this is like a summary of what's going to be in the main report. So it is a report kind of format though, this document. And it'll detail the scope of the project. So rammed earth external walls in a class 1A dwelling. Project details like your address, climate zone, your BAL rating, that kind of stuff. Key stakeholders, so you need to list who's involved. So your engineer, your architect or building designer, your building certifier, owner, maybe your builder or your rammed earth contractor. And then we'll set out what performance requirements we think are relevant to this project and what performance requirements we're going to address in our final report. What assessment methods we'll use, what acceptance criteria from the NCC will be adhering to, the required scope of supporting evidence. So often we'll require like some further architectural detailing or a certificate from your engineer, some additional evidence that we need to include in our final report. So we'll set that out in the brief. So this brief then gets sent to the client and to all the stakeholders, and everyone who's involved in the project has to read through it, and they have to either sign it off, like do a signature on the last page, or just respond to us in an email saying, we've read the brief and we accept it, or maybe we have some additional comments we want you to include this additional performance requirement or that kind of thing. And this is a chance for your building certifier or building surveyor to also have their say if there's additional things they want included in the report. So the next stage is the that's the stakeholder engagement stage. So that comes back, everyone gives us their feedback on the brief. Then we go on to doing some further research and analysis and writing up our final report. So this is the performance-based design report is the final document that then gets sent to your building certifier for approval. And that'll just go into detail about the applicable performance requirements, the proposed solutions. How we believe that the project meets these performance requirements, the assessment methods, the acceptance criteria, and we gather this supporting evidence. So it could be laboratory tests or fire tests or certificates from engineers and architectural detailing, all that kind of thing. So hopefully this will become a little bit clearer when I go into a real case study. The assessment methods that we use, there's basically 4 subgroups of these in the NCC. So these are the different methods that we need to use to show compliance with the performance requirements. Evidence of suitability, that's things like a code mark certificate, a laboratory test, engineer's certificate or report. Verification methods, they're things like tests or calculations or inspections that are either set out in the NCC, they have verification methods for each performance requirement, or we can actually come up with our own verification method. And if the building surveyor says, yeah, that's acceptable, we can use our own verification method to as an assessment method. Expert judgment, so that's just relying on the expert judgment of an appropriately qualified and experienced person. And then comparison with the DTS. So that's where, like for Randburg, for example, we do a lot of comparison to the DTS provisions for masonry. So that's where you can compare, even though it might not be a deemed to satisfy solution, you can compare to how it achieves the same level of performance as a DTS solution. So we'll look at this case study. So it's a stabilised Randburg partition wall in Melbourne. So it's a partition wall between 2 townhouses. The reason I've chosen this as a case study instead of just like a normal Randburg home is because we had to address these 2 additional performance requirements. So spread of fire and sound insulation, which you wouldn't really need to address in a standard Randburg home. But all of these other performance requirements, these are typically what we need to address for any kind of alternative wall system. Now, sometimes your building surveyor will just say, we need a performance solution that addresses structural, weatherproofing and rising damp. They're the 3 that we commonly just get for Randburg, but sometimes we might need to address all of them. So I'm going to go through these one by one and just talk about what assessment methods we tend to use and what supporting evidence we gather to put in our final report. So structural stability and resistance, essentially this performance requirement is saying that the proposed building is going to resist all the relevant structural design actions. So stabilised Randburg, it's not listed in the ABCD housing provisions. So that means there's no DTS method to determine the structural resistance. So basically for this method, you need to get a structural engineer to design your project. And they'll do their own calculations and modelling and rely on certain tests that have been done. And then the way that we show compliance in our reports is we just refer to your structural engineer's certificate of design compliance. So that's like a Reg 126 in Victoria or Form 455 in Tassie. Changes depending on the state. So essentially we're just saying the engineer certified it, here's his certificate. So weatherproofing. So this is just about, preventing the ingress of water through your wall system. There's kind of 2 components to this. The first one, so we do comparison to the DTS provisions for masonry. So the first part is to have flashing details. So we often request architects to provide us some section details of how they plan to flash the openings in the round earth wall. And we compare that flashing method to the deemed to satisfy provisions for flashing to masonry. The other part to it is we require on the architectural details to specify a siloxane-based weatherproofing system to be applied to the external exposed surfaces of the rammed earth. The reason we specify siloxane-based weatherproofing is because there's studies that show that it still allows for breathability in the walls while providing an appropriate level of water resistance. So that's things like your Plasticure and your Tech Dry Earth Aid for rammed earth. So yeah, the assessment method we use there is the comparison to the DTS and the evidence that we provide in the support. We refer to some different studies that are done on siloxane-based weatherproofing and the architectural detailing. Rising damp, once again, quite similarly, we compare to the DTS provisions for masonry. So essentially all that we require to meet the requirements for rising damp is to have a damp-proof course installed at the base of your rammed earth walls. And we'll also, if it's constructed on a slab, to have a vapour membrane installed under the slab, which is standard practice anyway. So yeah, all we really need to refer to there is just that these details are in the architectural detailing and they comply with the, well, they're comparable to the performance for a single skin masonry wall. Spread of fire. So this one, generally in a normal rammed earth house, you wouldn't need to address this. Unless you were building close to your like within 900 mil of your allotment boundary, or within 1.8 metres of another building on the same allotment. So because this is, for this project, it was a partition wall, the wall needs to achieve an FRL of 60-60-60. So that means it can withstand 1 hour of fire testing for its structure, integrity and insulation. So for this project, the client provided us with, this was a 400 mil thick rammed earth wall, and they actually provided us with an FRL test that was done on a 400 mil thick wall. And that test, it lasted 4 hours. It was 240, 240, 240. So that well and truly achieved compliance there. And we know rammed earth achieves compliance for fire. It's just about having the testing to be able to show that.
Does it matter where that testing comes from?
Yeah, so this is the 1530.4 test is the one that you need for your FRL. And that's been up. So there's a lot of old testing that was done on the previous standard. That's now been updated. We, like, not for rammed earth, but we sometimes refer to the old tests that were done on the old standard, and we just write a few paragraphs about like what's been changed within those standards and why the old test is still relevant. And we find that often gets through. But yeah, sometimes you will get building surveyors that needs to be done as per the new standard. Yeah. So wet areas. So rammed earth isn't listed as a deemed to comply substrate for the wet areas. So in your shower zones, they need to be waterproof. So they need to have separation from the rammed earth walls, whether that's a waterproof membrane and tiles, or some people do like a batten cavity to allow breathability, and then you have your aqua check with your billboard lining. And then outside of the shower zones, it needs to be water resistant. So we draw comparison to this clause. Again, it's a masonry clause where, if single skin masonry has been treated for water resistance, then that's acceptable. But you still need to do your wall floor junctions. So we need to show architectural detailing for your wall floor junctions and your flashings, and like coming 150 mil up with like a tile skirting or whatever. And we also, the way we compare it to this masonry clause is we require the siloxane-based treatment again. Sound insulation. So again, this is one that was only relevant for this project because it was a petition wall. So usually you don't need to worry about this one. we actually contacted EBAA looking for some tests about, yeah, sound insulation. I actually wasn't able to find the appropriate testing that was done to show compliance with the DTS provisions. So what we did in the end with this one is we engaged an acoustic consultant. Their consultancy had already done some testing themselves on the acoustic properties of Randburth, and they were able to just write us a letter looking at the architectural drawings and state why it was compliant with this performance requirement. So we actually relied on an external consultant for this one. Sorry, it's pretty repetitive and technical, but we're almost there. So condensation and water vapor management. We don't actually often get asked to address this anymore with Randburth, but when we do, once again, this is, we compare to the masonry standards and we compare to the clause that states that a single leaf masonry external wall, when it's constructed with a water resistant coating, then that's acceptable construction practice that complies with the DTS. So our job is to write a few paragraphs about how the siloxane based treatment gives you the same levels of performance as the water resistant coatings that are set out in the masonry standards. Sometimes with condensation and water vapor management, sometimes you can get pushback with this one. And that's where we go to the verification method. So we can use our own verification method of like a simplified thermal model of the wall system to show that you're not going to get a dew point happening within the wall assembly. And then building in bushfire prone areas. So this is actually the one performance requirement where there is a deemed to satisfy solution for Randburth. So if you get a building surveyor, saying you're in a BAL 30 zone or whatever, and they want a performance solution for it, you can just refer them to the AS 3959, the building in bushfire prone areas standard, because essentially this performance, the DTS requirements for this state that if it's constructed in accordance with AS 3959, then it's compliant. And there's a clause in AS 3959 that says that if any earth wall over 90 mil thick is compliant for BAL FZ rating, so that's your highest BAL level. So yeah, you don't need to worry about compliance for round earth in bushfire or any earth wall in bushfire areas. Yeah, that's so, yeah.
So in that, do you need, if you're in a fire zone or a BAL 40?
Yeah.
Would you need each wall of that level, or the walls that are away from the bushfire threat? You don't need that, or you're not sure?
In terms of the thickness?
Yes, yeah, as far as, or even the composition, so you've got Randburth facing the threat of the fire coming in.
Yeah.
And on the side, but on this side, you don't want the Randburth because of certain regulation and BAL and BASIC's requirements.
Yeah, so that's fine. So
and you have those different than because of the
yeah, for sure. So it depends. I think with your bushfire reports you get, where you get your BAL classification, you can get them detailed for what the BAL rating is on each side of the property, and then you need to construct in accordance with the BAL rating in that direction. So just because you're using a round earth wall doesn't mean you're BAL FZ compliant. There's also additional requirements around your windows and your eaves and all that kind of thing. But yeah, essentially the round earth component, you don't need to worry about compliance for that in a BAL in any bushfire prone area, as long as it's 90 mil.
It's fine with that.
Yeah.
But you said earth wall, what constitutes an earth wall?
So yeah, 3959, it just says earth wall. There's probably a definition actually in that standard for earth wall, because I would say if you're doing like an infill wall with a timber frame or something like that, that's not the same. Like I think we're talking about solid earth walls. And if you're incorporating straw and if it's a cob wall, I think a cob wall would be fine, but I'd need to look at, I'd say there's a definition for earth wall in AS 3959.
I need to expand on that for you, just to your point. The actual way it works, the outer leaf has to be 90 mil thick. So if you've got for instance, a straw bale construction, where you've got an inner leaf, the straw bale and the outer leaf, providing that outer section of wall is at least 90 mil thick will comply. It's not about the total thickness of the wall in general, it's about that outer leaf that faces the actual fire.
Outer leaf has to be the.
Yeah, but when we say we're talking, you know, carpet dope, mud brick, round earth, like anything that's basically consistently created out of dirt or clay is an earth wall, and it is actually at the bottom of the definition bracket in there, otherwise it's defined in the NCC. But the actual compliance side of it is the outer leaf. So if you had like a multiple layer wall, then it would be that outer leaf of the wall that we would be looking at. And it's the same compliance that gets it, it's just regular masonry as well. So, but to build on your point, when you have a bell rating that goes like northeast, southwest, you're required to comply with the highest level for the whole house. So if it's only FZ from the south, your whole house is FZ. But what can happen is in your bell assessment, there's usually a likely direction of fire indicator, and you can apply shielding to the walls that are not that are protected from that angle. So if FZ was from the south, then the northern wall could potentially be classified at bell 40, could step down one level. Okay, but even regardless of the way it steps up from ground to wall, but we're talking about the wall being compliant. In FZ especially, the detailing between the wall and the roof is going to be very important. And the roof itself has to be an FZ roof system. So there are very specific engineered FZ roof systems that are deemed to satisfy through code mark certificates. James Hardy makes one, and there's a couple of other suppliers. They're not cheap, but they are very, very hard to build properly. And they will trigger an extra mandatory inspection because we have to inspect the roof whilst it's under construction to make sure that all the mineral walking pools and stuff like that are in there. So prior to you closing the roof up, so the after the frame inspection, but prior to actually like sheeting or rendering or whatever you're doing as an internal finish ready to your roof, we'd have to come through and inspect everything to do with the ballast set roof. Will trigger another mandatory inspection. So
are you saying that a standard straw bale with just a thin skin?
90 mil.
Does it have to be 90 mil
if it's
now?
under 90 mil, won't comply.
Yeah, that's what I was asking.
Yeah.
So they've got to put a 90
Make the outer
mil
skin thicker.
render on it.
Render's considered a cosmetic enhancement, so it's not included in the law.
Yeah, straw bale, you look at the render specification, you need to rely on fire testing that's been done.
Yeah.
So like, yeah, if this clause wasn't in the bushfire code stating that earth walls greater than 90 mil are bell FZ compliant, what we need fire tests completed on a rammed earth wall, and we'd rely on that as evidence.
Yeah, 1530.
Yeah.
You mentioned that's a party wall basically. So
Yeah, that's a party wall, yeah.
So your photograph shows it as 100 and 400. You said it's 400?
Yeah, it might be a bit skewed. Yeah, that was a 400 mil thick wall. It might just be.
Wondering how that thin wall.
Yeah, I know, it does look like, I think that's just, it's a bit skewed. It was 400 mil on the plan, so.
The 2 stories.
Yeah, it's 2-story, yeah, townhouse in Melbourne. And we're seeing this a lot recently, like more of these projects coming through. And like personally, I think it's a really great use of render.
So with 40 mil is structurally sound, it's obviously more than 1 story.
Yeah, 400 mil, yeah, 2 stories, yeah.
So structurally, it takes on the loading for the floors and the roof?
I believe so. I actually can't remember what was involved because we didn't do the structural design for this.
Certainly do.
Yeah. And that's stabilized around earth as well, that's
You just need a detail, some sort of layering plate or mounting plate or
Yeah.
wall to connect your floor joists into and then just go.
Yeah.
Can I just ask about like cost variables?
Yeah.
Going through all of those different sort of categories that you just went through. If you're trying to, I'm not a designer, but let's say you're talking to clients about going down the performance solution route for a particular building system, you want to be able to give them advice that is going to know what, like, how can you tell what the price difference is going to be in the performance solution in terms of not only where you are, but what, you know what's out there and you know what's available for you to pull on that's already exists.
Yeah.
So I guess it's about coming to you first to say in a consult, this is like, if you're talking about, light earth or coal or anything that might not be as established as round earth.
Yeah. Yeah, so generally, like most of our alternative wall system, like most of the natural building stuff that we do, we generally charge pretty standard rate across the board because they're quite similar reports. I'm not sure how it varies with different consultants, because that's the thing, I think, because essentially, like it's consulting building surveyors or consulting engineers generally that write performance solutions. And I think you'll get quoted big rates if it's like a performance solution they've never written before, you know, because there's so much research and stuff involved. But yeah, we generally just charge a pretty standard rate for our performance solutions. Yeah. And it's about $2,000 a month. That's what it runs. Yeah.
What square openings?
I'm not too sure actually.
That's all they do is look at steel mounting blades.
Okay.
Around against it.
Yeah, okay.
In New South Wales or and other states that have this sort of system.
Yeah.
We've got a compliant development method.
Yeah.
Can you do this method and still go through the certifier and have a compliant development? Or does that then mean, oh, we're not doing the green to satisfy, therefore we have to go through the whole council procedures? Can you still do a compliant development and using different materials that's not in the national construction code?
Yes.
You can.
Yeah, so I think because usually in Victoria you get these done when you're getting your building permit, also your construction certificate. But it seems as though in New South Wales you need to get this stuff done earlier. Is that correct? Like for your planning permit, kind of like.
You can go through council, which takes longer, or you can have a compliant development, which is through a certifier.
Oh, yeah,
And it's like a rubber stamp of, well, that complies with what we want. But can we get that compliance of, say, a rounded wall through this being, not being the performance solution?
Yeah.
Still go through a compliant development is the question, rather than going through council. And
for sure. Yeah. So
that's good.
Yeah, yeah. Essentially for us, it's just your building certifier, your building surveyor. They're assessing the project, and yeah, for earth walls, performance solution is the avenue to get compliance. So yeah.
Good.
What about flood zone and stuff? Is there any type of compliance?
So because we do performance solutions for all sorts of topics, the only flood zone one I've done was actually having like a sunken lounge below the design flood level in the area. I haven't looked at flood zone requirements for rammed earth or any natural building stuff. Yeah, I'm not too sure about that. Yeah.
Okay. Oh. One last question.
When the design process with architect reach out for this performance solution?
So yeah, usually it gets picked up before getting your building permit or your construction certificate. So it's when you kind of in your final stages of your design's all ready to complete. Like you might want to try and find a consultant earlier on if you think you're going to have difficulty finding a consultant, just so it doesn't slow things down. It definitely happens, especially with rammed earth now, or if there's just like one component of the build where there's a rammed earth wall that gets missed by a building surveyor, and then they've already constructed it, and then the building surveyor goes, oh, got rammed earth, we need a performance solution. So we do write them in retrospect sometimes, but they're supposed to be written before you get as part of getting your building permit approved. Yeah.
So I suppose like you've mentioned a couple of things should be included in the detail, so yeah, maybe that's fairly.
For sure.
Yeah.
Yeah. And that's a good thing, like when we're working, with the same architects, then they get to know, okay, I mean, these are the things that you need to show. You need to have your flashing details, you need to have your damp proof course, you need to have your specifications for siloxane, weatherproofing. So, when we work with the architects on an ongoing basis, then they're aware that like they need, so they'll just start including them in their designs, in their drawings, because usually they're not flashing details sometimes, but yeah, usually all those details aren't necessarily in the drawings when they first come to us. So in our brief, we say we need these details.
All right, thank you.
Awesome, thank you.
We've now got Matt and Rhiannon. Matt and Rhiannon are architects. They have their own practice in New South Wales. Matt also teaches architecture at Western Sydney Uni. Rhiannon is a thermal assessor as well. So we've got a good understanding of our topic today.
And do mud fun as well.
And yes, and they do mud fun, which is actually a lot of fun. If anyone who's come to the conference before, you've seen how they've worked in our workshops. So it's always great. So they're going to talk to us about a roundabout home that they've built. So thank you.
Okay. We'll try and keep it brief. Normally we get you to sing a song or something if we're here under mud fun, as some of you would know, but we're not. We're under.
Sing anyway.
We've only got 20 minutes, so keep it brief.
All the economists.
Yeah, if we finish on time or earlier, we might sing a song, but that's anyway. We picked up this project in it was around, actually it started in 2019, and a couple came to us. They had a couple of kids. They were living in Wollongong at the time, and they came to us and they bought this property in Bathurst, and I came and talked to them, gave them some sketch design, sort of just critique their ideas, but they're very hands-on, very in control of their own projects. So our role was pretty minimal at that point in time. We didn't do any DAs or any drawings at all. They just did their drawings. We gave them advice. Anyway, I didn't hear from them for ages, and then 21, they called up and they said, "Oh, we really need your help. We built the house, which is where the pin is." They bought this property, really lovely land out near Sabala, just north of Bathurst. Bathurst is here, Spal's up there, and they built it, and it burnt down within like a month. Yeah, so it was a really tragic kind of scenario. And they called and they said,
They were in it too.
They were in it too. But anyway, that's a kind of Channel 9 type of story, and I won't go down that route, but pretty dramatic stuff. Anyway, they said, this time we want to keep you involved and go through the process. So we did, and we're much more involved. So if we go to the next one. Oh, look, so we'll go backwards. What we want to just talk about is the stars, and that doesn't mean bringing in George Clooney or Russell Crowe, although I did get them on the line and they were a bit delayed. So they might turn up later, but it's all over. But anyway, we're talking about the Natchez stars. It's a little bit more drab than that, and we just want to go through the process in reference to that issue, because this is about compliance and how we. So just briefly, we looked at what climate zone are we in. We're in climate zone 7. Climate zone 7's there from the NCC. I'm going to explain what the NCC is now after the last 4 lectures. So, but what we did do as a kind of a preliminary overview for kind of getting a feel for designing in this climate zone, which is different to what we're used to, is just go and consult your home and look at the design considerations that they have in place there. There are a few things there that we really had to tussle with, and it was an interesting thing that this isn't, architects and designers don't always get what they want. Like, you actually have to compromise a lot along the way, and our clients in this case had very specific ideas about the aesthetics of their buildings. So, for example, issues that we had to back down on were eaves. Like, we were trying to push for big eaves to protect the building in this climate. And the aesthetic that they were interested in was much more about European barns, which is fine and it is a fashion. And we just had to go along those lines. Similarly, things like having a black roof, where it was like, it's not really appropriate in this climate to have a black roof, but they really wanted a black roof. Not really appropriate when you've got a concrete slab and you've got potential for passive solar design to put a timber floor over it and insulate it, but again, that aesthetic overrode. So that's all fine, and these are issues that we have to kind of work through. So it's not all about us just getting what we want and actually having the best outcomes in terms of, say, thermal performance. Sometimes you actually have to back down, and the client makes those decisions fully informed. Then we, as we go through all these maps, it gets finer and finer that when you look into Natchez, I don't know how many, but this is climate zones. They have, for Bathurst, they have their own specific climate zone, 65, and a whole lot of data about that, which is like, you know, we just want to design a building, but we have to pay lip service to this, and we go a bit beyond that, hopefully. In a nutshell, it's a big site. There's a big site plan with beautiful views to mountain ranges and into like lands. It's just everywhere you look, it's just beautiful. And so they really wanted to capitalise on these views as a primary objective. That you know, if I wash up, I want to see that, and if I'm you know cleaning the toilet, I want to see that, and you know, so you know, as I walk down the hall, I want to see that. Like everything's just beautiful. So you just got to. Like the whole thing is just about.
And the dotted line is the old slab of the burnt down house.
What's that?
The dotted line is the burnt down house old slab, which we couldn't reuse.
Oh yeah. We really wanted to reuse the old slab, which was the only thing that was salvaged. But A, it was orientated a little bit too west, and B, it wasn't really capturing a few of the key views. So they made we worked really hard with designs to try to make that engaged, but in the end they made the decision to leave it and start again. And so it's really just a simple, this is stage one of the building. I'll just give you an overview of it. So it's just stage one. So it's just a bar building, you know, like a single bar with a spine running right down the length of it, like an elementary, one-sided elementary canal. And we basically are trying to maximise as much of the, you know, external wall to these views. And then when we get into this living area, you know, we want to wash up and look down here, and we want to make the fire, and we want to look here, but we also want to look here, and we want to look here, and everything's just lovely. So what ends up happening, which we've learned now, is we're creating a lot of surface area, and it's problematic.
There's a little attic.
And then there's a little attic upstairs as well. So this is stage two, which isn't built.
That's why the bedrooms were on the southern side, is
Yeah.
because.
So in that one, but they turn into those bedrooms that we just saw there. They turn into like a workroom and a garage. That's right. We turn those kids' bedrooms
there it is.
into a garage in stage two. So that becomes a garage. This becomes a study, and so they're really just utility or secondary type of spaces to the south. And the next wing that gets built up here, again, up onto the north side, we're maximising all the bedrooms and the bathrooms, and we think we're trying to do the right thing in terms of making this, you know, this dwelling engage with its exterior landscape and do all the, you know, make all the connections that we learnt at uni, and we looked at Glenn Murcutt's work, we look at Rick LaCastria's work, and all these great architects that do these really kind of thin buildings that are engaged with the landscape. And we're trying to do that, but the natters kicks us up the arse. So, right. So this is what we're actually trying to say. This is designed before October 23, when the goalposts changed. So before this, we were, you know, basically any house that we design, as you were saying earlier, we could get it through. We could get compliance with BASICs. We could get compliance through NATOs. It wasn't that. You just had to add a bit more, add a bit more, add a bit more. But now it's different. And this one was one of the last that bolt through the gate. It got, you know, let's get going down.
Okay, so
yeah. So
well, no, the reason it was the rammed earth wall choice. They used hempcrete. Loved the surface, loved the materials inside, and it was partly the reason it burnt down.
Yeah.
They didn't want to use that again, and you, from the earth building thing, suggested rammed earth. They loved it. We're doing that. We're doing that. We're definitely rammed earth.
So it's because of you guys that we had this problem, basically. We came away from all the workshops over the last 5, 7, 6, 7 years.
You've got to do it.
And we're like, this is a really good material. And they went and looked at rammed earth and like, oh my God, we love this. We want to have it inside, we want to have it outside. This is the most beautiful looking material. It was about the look of it. It was really about the look of it, not about the other characteristics. So it didn't, as you say, we didn't have to push very hard to get the clients to get on board with it, but it becomes a problem, as you will see. So anyway, it's prior to October. This is like D-Day for architects. October 1st, 20. We should actually have a national day of, I don't know, reconciliation or mourning or something. But it's October the 1st, 2023. We had projects like these houses, and we knew this was coming, and there was no real guidelines as to what it really meant. And it was like freaking out, trying to get approval, like trying to get these, not this one got through. Because what happened was, anyway, I'll tell you the story. So what happened was, actually, we're using a slide, we want the.
No, this was, so the client got the consultant to do a NATO's
Because
consultant.
Rhiannon wasn't accredited at that time.
No, so the NATO's consultant came up with 4.8, said on the 300 mil boat, because all those long walls are all round earth. 4.8, you're going to have to insulate the walls.
Oh, sorry, we should just go up and explain the construction.
and then-
Can we just go back? Sorry, so this is where the round earth is, here and here, and we'll just talk about that one because that's the second stage. And then everything else is stud frame, and the slabs waffle pod, just so you got an idea. So it's just these two north facing and south facing walls. So sorry, go on.
Yeah, so he recommended insulated.
It didn't pass.
It didn't pass.
It didn't pass NATO's. It couldn't. It nearly did, and the assessor said it needs to be insulated around earth. So sorry, go on.
So the prices came in, and then the client said, "I think."
Yeah. So basically, it became a financial decision, right? So that client knew that they'd have a much more comfortable building with insulated around earth, according to the NATO's assessor. And they then went and asked the round earth contractor, because who they were liaising with, to give quotes, and they got $197,000 for the 300 mil uninsulated, 297,000 for the 450 mil insulated.
That was back. Yeah.
So the owner basically says, "What do I do? You know, I prefer to save that $100,000, right? Yeah." And so they're very hands-on again. He said, "Well, I did the basics before. I'll do the basics this time. I'll just forget the NATO's. We'll do the basics, do it itself." And they put it through. He did it, and it passed. So it passed with 300 mil solid round earth uninsulated.
At both stages. So he did both stages, and it passed. So that was at the time, I remember at EBAA, where they were saying, well, the basics tool's taking more into account, or at that time seemed to be, it was all very confusing. I was like, anyway, that at that time that he got that through.
Anyway, so we get we just rushed. So we get a bunch of basics. That's kind of a summary of all the basics. We're not going to go through this, but you can see up here somewhere it says 300 millimeter round earth. Down here, sorry, 300 millimeter external walls, 300 millimeter round earth, additional insulation, nil, pass. So we're thinking, oh, that's pretty good. Like we did okay. So let's move through. Now, for this, so they built the house and they moved in and they lived in it for whatever it is, 2 years. And we've got a little bit of anecdotal sort of feedback on it. That's not great. But for this seminar, when Rhiannon talked to you guys and basically, can you do something about regulations? We thought, well, let's run it through the model using the Hero software for under the current 7-star requirement and see how we go. And we did it exactly as it's built. It's got to meet 7 stars and it gets 3.2.
But that again, it's hard to know exactly what the original, when I looked at things, some of the things were, depends on what figures were put in. It's also the client put in the basics. So it's not the same person putting the same information in, not the same software tool. But it's still quite a big difference.
Yeah, but I think there's another slide which this is that one.
So the previous one was 4.8 in Burrs Pro.
I don't know whether we used, was it Burrs?
I think it was Burrs.
Yeah, it might have been Burrs.
And this one's 3.2 in here.
Yeah.
It's not, so fundamentally when we move from 29 to 2022. So matters actually, we had to redo it. You were saying 35, we have to make one correction.
That's right.
So that's that.
That's a huge, that's not, the energy target doesn't have any impact on your star rating. The star rating is actually the performance of the building. The target's been changed, but the weather files changed. So what happened is how it interacts in environment change. So what it's saying is, for the current weather, the building needs more energy to actually be comfortable, and that's why there's been a downgrade.
Yeah, so it changed, the climate files changed, and it was on the cooling side as well, so it was getting too cold, I suppose was
This biggest pitch
Okay, oh, that's interesting. Yeah, that's what we didn't know, but I was thinking it must be, it could also be the input and the software, but it all probably was the climate change.
But also no, that's it.
Yeah, yeah. So that really does, that's good to hear.
All these
that.
numbers
That's what
just
we
in my
thought.
head in, just like, oh,
Yeah, that's what we thought.
Going to 6 or 7.
What's that?
7 climate?
7. Climate 7 was.
So
65,
65,
Natters,
the
yeah.
Natters one, but I think it's
Climate zone 7 it was.
climate zone 7 and then climate, yeah. All right, let's go. Yeah, let's go. So what we did, like, we just sit there and, like, if it was a real project, we would seriously be freaking out. Like, it's like, oh my God, but because it's built and it's all done, it's just theoretical for now. It was cool. We're sitting there this week and we thought, let's run it through. Well, what do we do? What would we do? And if we go through the panic scenario, imagine it'd be slightly different emphasis on what would we do. There'd probably be a few expletives thrown in there as well, but we don't have to resort to that right now. So the first thing we do is we look at, well, let's just, from what we think, we could look by room, but we didn't have time. Replace timber floors with ceramic tiles so we can just get that thermal mass back on the floor rather than insulating the slab. Wasn't much of a change from that, a slight improvement. But the big one was adding the insulated rammed earth back in. This time we just did it on the 2 southwest walls. And hey presto, we go up a whole star.
Yeah,
Right.
the windows were already sort of maxed out as the argon filled double glazed,
Oh, yeah,
good quality
yeah.
things anyway, right? Like that was assumption right from the beginning.
Yeah.
Yeah.
Let's go on to the next one. So we're still shy of 7 stars. Then we use the zoning. There's these daytime and nighttime zones within the bureau or the Natchez parameters. And one of the things we did was just play with these zones. So we, instead of that hallway being a daytime zone, we extended these rooms into it to halve it basically the area of the daytime zone. Just sort of working with the software really, and we get a 0.2 of a star. We go up. Okay, next step. Okay, we're still not there. Oh my God, we're still not there. Step 3, we go, all right, we had a cathedral ceiling in this cross section through the living space. We had this big cathedral ceiling up here.
We thought, oh, that's going to be, in other projects, that's really made, oh my God, like the high ceilings are a disaster in terms of cold.
And in the Your Home recommendations specifically said no voids or double height ceilings. Specifically for this climate zone, we're like, and we're putting in a cathedral ceiling.
But all the ceilings are 3 meters, so that they're tall.
So we go down, but funnily enough, we go down a 0.1 of a star. And the reason that said was that we're increasing the cooling load in summer. So it's this juggling act.
So you're going from 3 and what, 5?
We went from 4.4.
So in terms of cooling load, it was 3 before.
Yeah,
Which is nothing.
Don't know.
So you might be going up.
Yeah, tiny bit.
Tiny bit.
They're punishing you.
Yeah,
for
that's what we
Yeah,
think.
so it's
Otherwise,
like
we'd like
this
for all
is the
that.
real problem.
Yes.
Yeah.
Yeah. Yeah.
So then we keep going, we're trying our best. And we go, okay, well, let's throw, we'll insulate the garage door. Well, it might do nothing. We try it. And then we added insulation to the northeast walls. And then we go up.
Clocking up the money.
Another star. So
Not costing us anything.
we're improving significantly just by adding that. And then, yeah, we add another 100,000. And then step 5, we changed the insulation.
Yeah, just to a chunkier insulation.
We get 5, 7. Oh, and at that stage, I said, what would insulated cavity brick look like at this point in time? Because we actually, since October 23rd, had a lot of success with big increases in star rating by putting the thermal mass, as you were saying earlier, inside, like turning all the interior stud walls to brickwork. It just, it's massive increase.
So it is in the,
it's in the,
in her software anyway. Mass is, I mean, we talked about it before, but mass, we thought it wasn't playing a big part, but putting mass inside well, that's in our Illawarra kind of zones and Sydney zones, definitely improved those houses, but it did in this too.
But the cavity brick, as you can see, is actually performing worse than the rammed earth insulated, which we thought was interesting.
Oh, in terms of the cavity brick and the rammed earth? No, cavity brick was, well, you can't, doing 100, it's not practical. Like 100 mil, you can do in rammed earth, but you can't really do it in brick. Can you? I mean,
Yeah.
I don't.
Okay, so in this star rating system in NatCos, for example, you calculated NatCos, so they don't take into account anywhere the air change rate, like how airtight the building is that?
Yeah, I think it's all built in. See, this is we're scrambling, or yeah, we need to be the engineers that understand it, but yeah, it's very complicated, but it is built into the software.
But then what do you assume? Like, do you say we build like a passive house, so we have
that's
lower door tests and air change rates, do some code? Is that any
yeah, you can do the passive house system through, you can actually do that through the basics tool, but no, this doesn't do blower tests. No, they don't even, you can't put it in, there's nowhere to sort of blower test.
Yeah.
This is regulatory mode. This is your this is the main.
Maybe, but I think at this point it's going to be like about anywhere between 8, 12, 18, or depending on the. So it calculates. So every window that you add increases the leak. Every downlight you add increases the leak.
Yeah.
So if you have no downlights in your building, your weakness will be very. It's not a block.
And whether it's sealed downlight or not,
or it has cathedral ceiling. So then we're rearranging the deck chairs on the Titanic here, basically. we put insulated, we put the internal mud brick walls in 150 mil, rip out all the stud frame. We get 0.1 of a star. We're still
better.
It's getting better. Then we like go, okay, all these big windows, we're going to get all these lovely, great views, and everything was like we just reduced them down to arrow slots.
No, they're not. They're fine. They're fine.
We're fighting NATOs, you've got to get down to arrow slots.
Yeah, that's right. That's right. We're fighting NATOs, we've got to shoot it. Yeah. So 6.2 stars. So we're within QE now of 7 stars. We're getting there. And then we just gave up.
Yeah.
That's so close. Yeah, really close. So then we're thinking, well, what else could we do? We could provide eaves to probably protect the rammed earth, which would have been a good idea in the first place. Relocate the garage to a separate structure. So now we're redesigning it.
It needs a redesign. The bar
reducing the ceiling heights throughout. We could do something like this. Locate the sleep. Okay, so we realised that what was really problematic was basically all of this surface area is the problem, you know, and if we actually did that and blocked probably 70% of the views, then it would probably be a brainer. In fact, if we go to the next slide, this is a job we're just doing at the moment in Wollongong. It's not in the same climate zone, I know, but we ran a model of this, and if just in a nutshell, it's just basically similar sort of thing, which is just living spaces to the north and sleeping and utility spaces to the south. Okay, so there's a couple of rooms that aren't so great in terms of getting sunlight and so on, but they are sleeping spaces, so it's less of an issue. We run that through Hero now with way before we go to DA, like at the sketch stage where we've actually got a layout, we say to our clients now, we have to do a model. We have to do a thermal model now. We're not waiting until we've got all our DA documentation like we used to. We actually run it through now to make sure we're not barking up the wrong tree.
Yeah, with that other scheme, you can just angle it, just change it. It's an open site. If you angle it like we've done it, where we've just moved it 20 degrees there or 15 degrees a little bit around. Oh, no worries. So
and it's fine.
Yeah, so the emphasis on the rammed earth, the particular material, as other people have said, there's so many other things, and we shouldn't be put off using earth building if there's so many other parameters that you can change to make things work and comply before worrying about the materials exactly.
Did you try swinging it to the northeast or something like that?
Not that one, but we have done it on another project where I was
pretty well perfectly orientated, so we didn't really have to worry.
Yeah, but we did on other projects.
But with this one, we did this at the scale, and it's straight away 7 stars. straight away. And so it's got so much more to do with the layout and the actual planning of the building, rather than tinkering with the bloody materials, you know, like you just get the layout right, which we're learning a massive lesson from this. But when we look at this plant, like when we look at this, it's really compact. It's got, as I say, living space to the north, sleeping and utility spaces to the south. It's a double-sided hallway rather than a single-sided hallway running through the whole thing with all that, you know, heat transfer going out of the hall. It's got, you know, all these things: insulated concrete slab floors, insulated frame floors, etc., etc., etc. I'm going to read the list, but we ran it through because we're doing this with reverse brick veneers. Dickson wasn't running it inside to get thermal mass again into the interior of it, basically.
This is all done with geotech stuff, and it's steep and all that, so we didn't.
We ran it, and we ran it with uninsulated rammed earth as a model, and we got 6.6 stars, and then we insulated the rammed earth, and we're like cruising 7.2 stars. So, yeah, so that's basically what we got to. What's the next slide? I think we've got So we just thought we'd just quickly, while we got the chance, it's kind of an interesting build because it's really simple, the whole thing. Like there's no complexity to it. You know, like we got and you can see the countryside, why they wanted to just open it up to these views, because it's really spectacular. So we put a waffle pod slab down, and then they filled the truck. I can't remember what species. Probably some experts here would know. I can't remember what it was, but a big old eucalypt they had on a neighbour's house. And they got a mobile mill in and milled it all up and took it all off on a truck. And then, anyway, that's on the way to another story. And then here's our first panel rammed earth going up. We've got engineers' details showing starter bars going up into the rammed earth.
He hadn't worked with rammed earth before.
He didn't know rammed earth at all, this engineer. And then, and then we can see here these bits of timber that they've milled just lying around, which doesn't look very kind of good in terms of termites, but up above you can see formwork for the rammed earth beams, and then we keep going. Oh, that's a nice picture. There's more nice pictures, and then these are just the engineer's details of the rammed earth beams over the sort of lintels, where we've actually put reinforcing steel in the rammed earth.
Someone was talking about that's quite hard to actually do around the cages and stuff.
He was really worried about this beam. This is an elevation, sorry, and because it was a 9 metre span with a post here, but it would actually bulge out, and we'll talk about that in a second. That's what they built out of the timber. These big trusses with these embedded nailing plates, and there's his details. There's his details. Anyway, that was his detail. And they got the crane on the site. They built all the things, and up we go. Yeah, and so then they're just dropping all the trusses on top. Like it's really simple. You build the platform, you build the 2 blades, and you just sit the trusses on top. And I don't know. I just like the simplicity of it. And keep going. Where are we? Yeah, that's blah blah blah. Nice pretty pictures. No, this is Bathurst. And then this is this structure. This is the solution to this beam kind of bulging out. Where we had a pergola out there, and and you can see that we don't have eaves, and we've got a black roof. But hey, you know, that's the sort of thing that happens. And then we've got this pergola structure which we use to buttress the worrying beam. There it is. There.
It's hot. Just ask a question. When the place burnt down, did they put the steel in as from a fire prevention? Like
no.
The steel rebuilt it in a way that one would hope fire, as it comes again, they won't get burnt down.
Yeah.
So
the fire was internal house fire.
Oh,
it wasn't a bushfire.
Oh, wow.
It was the hempcrete. It was the hempcrete caught fire.
Makes a difference.
We keep going.
It was a fireplace onto the back of hempcrete, and the temperature, he had it cranked up, and it sucked into the fibres. This is the analysis afterwards. It sucked through the fibres, and because there was a stud wall outside, it was fanned by a lot of wind. Like it was quite a windy night, and they, you know, and the fire was sucked through and went up, and they didn't notice. They said it was glowing red, the whole roof, but it didn't. It just collapsed, like the whole building went down, like terrifying.
It's supposed to be fire.
Yeah, but it was a particular situation of hempcrete. There was a timber wall fanned outside and the fireplace on the hempcrete.
Could you have experimented with solar to change the capacity? So I once had a project where I wanted to change the water heaters, 8 water heaters, and I changed it to electric from heat pump. So to make the basics work, we just the solar.
Yeah, but the basics needs to thermally tick the box first and then you work on the energy. So you can't go below the stars. You have to have the level of thermal performance before you go into the energy costs of balancing out your solar. You can't max out on solar and have poor performing walls. No, you've got to do that first and then.
So their answer to is pretty simple because they've massive photovoltaic solar array on the house, but also on the existing shed. So any shortfalls in the thermal performance, they're just supplying it.
And they put the fireplace really far away from the wall.
Yeah.
Right in the middle.
But anecdotally, they're saying this house is actually the heater, which was going there, the fireplace, which is going here, actually keeps the house warm itself. They found that, funnily enough, like that end wall there is stud frame here, that's freezing cold. But in winter, but the round earth is warm.
So they're picking up on that lag, and it's the feel of that. So his anecdotal talk is that the walls are warm, and the stud walls, which are really well insulated, are cold. Which is, I suppose, that thing you were talking about on your skin. That's how it feels.
Yeah. And they've got an attic as well up above, and they said it's just unbearable. Like it's just too hot.
Yeah, and none of the sun shading was all left off, and I don't know how the certifiers got through, but all that was required. There was sun shading on all these windows, west facing, vertical as well, and all of that must have cost too much, or it hasn't been done.
So the late summer sun, we modelled all this actually way before, and we actually have designed green awnings on like vertical sunscreens on these western facing windows, and they still haven't put them on. People run out of money and stuff. And they said, oh, in the afternoon the sun comes baking through those windows. Like, yeah, that's right. They know that. They know that. It's something, they know it. It's something they have to do.
Sometime they'll put it on.
But they said that's the real source of the overheating. So if once they do that, it should help to regulate it. But I think also thinking about some of the lessons from this morning, definitely protecting that round earth and with a bigger eave would have been a better outcome. Just listening to stopping that heat,
oh, they did say there's a lot of leakage, so it might have been. And we were going to ask that of people, the contractors and stuff, but perhaps the round earth moved or shrunk, or there's too much gap. They're saying it's around windows, and it's the ceiling, and even some of the joints and things are not, or the round earth to the roof is not well sealed, so that I feel like it's drafty in winter. And I was like, oh, okay. Everything, yeah. So it's just a construction thing, yeah. Okay. It's the joint, yeah. He's saying the joints, but is there something that we got? I don't know. Is there something that contractor didn't do, or is the silicon thing? The span.
What was that?
The span. Oh, you mean across that way?
Yeah. It's
Seven? Is it?
No, it's about it's very thin. I think it's about 5.5 meters or something like this. Yeah. No, that's fixed.
So there's no way for the hot air to get out.
Yeah, it can. Yeah, we haven't got the photo, but behind us there's a mezzanine grill, and there's so air can go through the attic, and there's a vent window at the other end. So yeah.
Yeah, that would have been good. That was supposed to be more window there.
Yeah, but it's kind of interesting, to look at the process more holistically and dealing with, aesthetic considerations and the, thermal performance and, the construction
And these windows are timber windows, but they look aluminium to me. Like, it's interesting. The outcome is like the painting it black and making it look, you know.
Yeah, I thought
it's
they were
interesting. It's
No, they're not. They're hardwood. They're all argon filled double glazed windows.
yeah,
as
they're
well.
full on windows. It's like they're not. Yeah. All right. That's it. Thank you.
Okay, so this is a house I did in 2016. Some people have already been to this house and had a look at it in earlier years when we were down at Bamarang. So the design brief was pretty simple for this one. Not a difficult client like the last one. This one needed a small building, simple, beautiful, 2 bedrooms, blend with the existing Colorbond stable and outbuilding she had, maybe a bit of barn life. Most importantly, it needed to be instantly comfortable on arrival on weekends and from Sydney. So I'm sorry, I should have given you 2 already. Is that number 2? No. That's, it's not working. Didn't touch anything. Oh, that one. Yeah. Okay, thank you. Don't come with that. So I instantly informed the client that winter was going to be the issue. Summer, spring, autumn would be fine. She could come down any time, and the house would be pretty comfortable. The winter there's going to be a shortfall. That's all the buildings I've ever built in the Shoalhaven. That's a problem. It's a winter problem. So I suggested to her that if we wanted to have an open building. She's a country sort of person. It's a magnificent site. Good ability to orientate in any direction. But north was fantastic and easterly views and all views were brilliant. Which is, you know, I was thinking wasn't going to resolve the problem with arriving to a beautiful comfort by having a mobile app and sort of pressing a button and starting up the air conditioner. It was always going to be a passive low energy building. It's like outdoors looking to the east and the north a bit, but there's ocean view. It's quite lovely. So I'm going to jump through this, but so she was happy to have a wood heater, and I said, look, if you have a wood heater in here, it'll warm it up nicely. But the thing is, you arrive on Friday, it's going to be a cold house. It'll be lovely by Sunday afternoon when you're leaving, and then the house by itself is going to be beautiful all way halfway through the week until Wednesday, and then it'll start cooling down. Back Friday, it'll be cold. Start again. So I said the best way to do it, I was thinking, would be to put a conservatory on the north side. So I did a sketch, pretty simple plan and elevations, and then I passed it over to Mike Dobson, Steve's son from Western Australia, and he tidied it up, and I don't like CAD. He was able to make the round earth panels very easy and economical, practical layouts. It was a useful exercise, and Mike was wonderful to work with. So I put it through BASIX back then, and there wasn't a problem. It was the old BASIX. It was friendly to earth buildings, and it passed, no problems. we also engaged E-Tool to have a look at EBAA was interested then in the life cycle assessment of earth buildings because we've had great success with Mudbrick one retrospectively looked at in given a life cycle assessment, and they're all coming out sort of close to 100% full life cycle zero carbon, and some of them beyond. My place was beyond zero carbon with a simple addition of photovoltaics and a solar hot water system. So we wanted to look at that with this building as well. And unfortunately, I didn't get a certificate on it because the photovoltaics weren't put on straight away and the heat pump wasn't put on straight away. And so we never got the final assessment done on it. It'd be interesting. I think it would have been up a bit on my place because of the double glazing and things that went into it. But that's just a few views of the building. But Faye, when we're doing the life cycle assessment, she was good to work with because she was talking about how when you put in double glazing, your embodied energy goes up, your operational energy comes down. But she was saying there's going to be a balance in the full life cycle assessment of the building. You don't want to build up the embodied energy, which is an instant carbon bomb now, and then right now and then over the life of the building, the operational energy is saving you a little bit. So you've got to look at both. Unfortunately, we're looking at one thing at a time in Australia. So anyway, it's achieved a simple barn-like look, and it's quite nice. That's a southern view. That's inside. So what I like to do with earth buildings is sail them. It's how you operate them. They're naturally ventilated. My house and Ray's house and a lot of other houses are ventilated all the time. Not when we want to conserve energy. They're ventilated all the time. And conservation is a different thing with earth buildings. You've got that ability to naturally condition it. So the thermal mass is able to moderate air changes, and it's actually how they operate. So I think in NATERS, with set ventilation logic and things like that, it doesn't really reflect how you operate the house. So you don't get a real accurate prediction of how they work in reality. Anyway, the client said it was absolutely beautiful, exactly what you wanted. We used a lot of recycled timbers where it was seen, and some architectural plywood, and so it is a very comfortable building to be in. It's May, I think, we took that photo. I visited there and took some photos. It looks like my son and I live there. We're out in the outside area with the doors open, and you know, it's 2/3 into autumn, so it's, you know, not bad weather, but cooling down. But the house wasn't heated or cooled for 2 years. The client moved in, came down on weekends, spent COVID in it, and it was quite a comfortable house without any heating or cooling. So the way you operate this house is to, you know, I haven't showed them really.
You talk about the right picture.
What's that?
You missed to talk about the right picture. Got the last slide.
Go back.
Second.
Going down a route to the right side.
You want me to talk something about
I
that?
just don't understand what is that, the second picture of this.
The one to the right.
The other picture?
You have construction.
There's just that's during construction, but this hallway is big in actually controlling the house. That window up there, that tall thin window on the right hand side there, if you crack that open, that draws air through and out, buoyant air rises and out. The stairwell's in there, so that is a critical window that you're looking at. Does that help? It's during construction. It's just a dramatic photo. Okay, so you can see how the sun, all these photos were taken at that time, 2/3 of the way through autumn. So you can see the rooms, the living room and kitchen dining area is pretty well lit. And you can look up that left-hand side, you can see up the stairwell and that little window at the top. That's the one that will drive the building. So the heat is trapped in the right-hand photo there, which is the conservatory. And the glass sliders that separate the house from the conservatory open here. The surface sliders, they've got the brush seals at the bottom, and brush seals against the wall, and brush seals at top, across the top. So they do sort of close it down a little bit from the conservatory. Conservatory is all single glazed. Then you've got single glazing and those dividing doors, but the gap there is like it's a break from outside. So it's like double glazing in some ways, I guess. So sorry, I'll get there. So when the doors are open, you're actually getting a bit of a Tron wall effect. See that the sun goes in through the conservatory, and it's sort of magnifying onto the rammed earthing behind there. I think that's my guess. But
is it the natural clay colour too?
it's a sandstone rammed earth, so this reconstituted sandstone. So it all works on sun angles and everything pretty correct. You can see there that the winter sun's coming. The conservatory pops out in the middle, but most of it's that narrow conservatory. So the sun will come right into the floor of that living area. The sun angle in summer is cut off pretty well by there's not much of an eve there. But, in summer, the conservatory is a veranda, so it's completely open. All the popper windows at the top, the louvers, everything's open. So it's just a free flushing veranda in effect. Sorry, it's all louvers, so it's open 100%. Sorry. Oh, it's still there, but it's all open, so the air's just running through it. And you can close or open those windows behind, depending on whether you want. If it's a lovely breeze, nor'easter blowing, and it's quite pleasant, let that through the whole house. Open up the back windows and let it through. If there's a southerly blowing, you can run it the other way. So it's all about just sailing the house how you want it, really. So it's not about sealing the house. And it's got good cross-flow ventilation. In the living area, there's a window, EV3 there. You can see that. Open that up, you'll get flushing right through the living room. You can let it go up the stairwell, open up the hallway, let it flush out up through the top bedroom window, or up the stairs and out the window in the that part of the house. So compliance. So I had a problem with retrospectively complying with the OC. In BASIX, when I originally did it, I had put in timber window frames, and in the end we chose aluminium window frames. And I don't know whether I got in there and changed that particular side of it, but I had to sign off on BASIX. And I didn't want to just ignore the fact that I changed the windows. I possibly could have got away with it. But I thought I really need to show compliance with energy efficiency by modelling it in NatHERS. So we were looking for 5 stars because it was an older building, and we got 1.7 stars. So in Hero, and this was a bit of a concern. surprised me a lot. But, you know, when Phil Harris from Troppo says that a 0.5 star house is brilliant, and if you get 7 stars, then it's a terrible house, it gave me a little bit of confidence, but I was on the right track. But I know the house is a very comfortable house, and the client is not one to put up with fools or discomfort. And she lived in it for 2 years without a problem. And I visited the house in winter; it was lovely. I visited in summer; it was lovely. So I know it is a good performing house. So what do? We've got a terrible star rating. It's not 5. So the guy that did the assessment for me, Alex Slater from Building Physics, suggested that we played around with it a bit. I said, "Can you trick it?" He said, BERS Pro was used to establish the life cycle assessment that was done by Faye back in the early days. She said, "This is a problematic design to model in NatHERS because it can't deal with the conservatory." And then Alex Slater said the same thing. And I talked to Don Chen at CSIRO, and he said there was a problem with it. With this particular building, it couldn't be modelled easily. He could do it, but it couldn't be done easily in NatHERS. So Alex suggested that, you know, after we tried tricking it by saying, "Okay, let's model it in winter as if the conservatory is all closed and you know, a conditioned space or a non-conditioned space. How does it work out with the heating load? Does that fix it? And then in summer, maybe we'll say it's a veranda. It's a non-conditioned veranda space. And then look at the winter and look at the summer and see if we can sort of come up with a performance-based solution based on that." And it didn't really help us much. And he said, "Well, I've got another tool I could try and model it in, and that's Passive House." And I said, "Look, I'm not a fan of Passive House. I'm sorry about that. Actually, not a fan of the seal-up insulated box sort of thinking. But you know, I'll try anything at this stage." So he put it through Passive House package, and I don't know how he did it. I don't really care how he did it, but the results were favourable, and the problem was solved. Getting an OC, and so the client was happy. So this is. Go back. You want to start being critical? Sorry? Yes. Yes. So you want to have a go at that one?
So no, it's actually doing what it's supposed to do.
Sorry?
I wouldn't thought these numbers are looking awful. That's what numbers are.
I can't hear you, sorry.
No, the Passive House numbers are looking okay to me. It's looking sensible because the cooling demand is pretty low,
Yeah.
which is what it should be.
Yep.
And the heating demand is there because you have a lot of mass in the house. And mass is a heat sink as well. So NatHERS is not just about, it's not the conservatory that's the problem for NatHERS.
Yeah.
It's a lot of other things that's causing the rating to come down.
Yeah.
So I wouldn't put it down to, that's not the only limitation, is what I'm trying to say with NatHERS.
I've got problems with NatHERS.
Yeah, there's other problems that's making it come down because conservatory cannot make a 6-star difference.
Yeah.
You know, it's not the conservatory.
Oh, I don't think it should have been 1.7 stars in the first place. I think it could have been more like 5. But just going on my place, this is I was moving on to my house. It's an old mud brick house, and it's 3.2 stars. I've had discussions with Tony Isaacs, retrospectively modelled this as 3.2 stars, and then recently we've looked at it because it's an old building. It's got 1.5, state of the art
sort of insulation in the roof. Single glazed, beautifully leaky windows. Probably I couldn't afford as many windows as I wanted on the north side, so he's optimised that. We looked at it. I said, NatHERS doesn't believe in deciduous pines and they're a problem for them, and trees and things like that. But we looked at it again. I said, look, 7 Stars is coming along. How are we going to cope with this? Say I wanted to build my house again. What do I need to know? And so we upgraded the roof insulation to what you'd standard now. So maybe R5 bats or R4 bats, which I always put more in than need. And then Anticon 1.5. So you've got a good insulation of the roof. I don't think you said you don't need to go to double glazing, but I'd consider double glazing if I had to. And just a little bit better, more glass from the north. And we're sort of getting it up and gradually getting it up without turning it into a brick veneer or anything like that, or reverse brick veneer, mud brick or anything like that, which I don't like. And we tried optimising the characteristics of the wall. So we've put in, I'm not sure if you're aware, but we've got 5 different densities of earth in the NatHERS library now. So you can, and that may have helped with the house at Bathurst too, if you could introduce lightweight aggregates into the mix. You can actually get and even thickening the walls and on an inland climate can change things. But we tried all that and we're getting up there, but it wouldn't really go until we put in a waffle pod slab under it to decouple. And I thought, you're going too far, Tony. I'm not going that far. I'm not falling it down the waffle pad.
Your rock slab always forms and a waffle pod. I don't see why you should do that.
Yeah, that's what I
Unless
thought.
actually your cooling is your heating requirement is so high that
Yeah, the heat was a heating requirement. I don't have a cooling requirement. NatHERS has always said
it's cold.
It's beautiful to me, but it's cold to them. So that's the problem. It's the NatHERS heating and cooling set points is a problem. Anyway, so he said waffle pod will get it over the line, and I said, well, I'm not going there because of the toxic foam, and because we've got heating, warming climates, and I've already modelled into the future. I know this house inside out every possible way, and we've done modelling into future climates, and my heating load disappears in 20 years. I won't be here to appreciate it, but someone might be living in the house and it'll go away. So if I insulate and decouple from the ground, it's not a good thing for the warming climates. Anyway, so we're that's just I've had it monitored for a year with an ear at near Pathway UNSW. The monitors everywhere, the CO2 sensors, and it's not always like that. And sometimes it's slightly cool, and I put in my report, I'm not cool at all. I don't know if any of you takes that on board, but it's never, the CO2 monitor has been perfect all the time, except when we had a crowd of people in the kitchen dining family area. We had the muddies over for a bit of a meal, and every gas burner was going in the kitchen, and there were lots of people breathing and talking.
That's good.
Excited, drinking red wine, and the temperature. The temperature came up, but the CO2 went up a little bit, and never over 1,000. It's always good. It's always not near perfect, but down to sleepiness. But I put in the exhaust fan to
resolved that. It's never been a problem since, even with the crowd. Lots of red wine and laughter and happiness and talking. So that's resolved it. So we're back to perfect indoor air quality all the time. No heat exchange. So this is that's the future of warming climate sort of modelling we did earlier. See at the moment in that Tonglong area, you know, I've got a fair old heating requirement, and actually this is not my house. This is another house, but it's in my area, Mudbrick house. Because my cooling's never 20. So this must be a different house at Tonglong. You can see that the heating load drops down all the time as the house moves up to Harvey Bay. Without me going on holidays up there, the house will head that way. So we've got to look at the climate change resilience. It's a big thing, and also passive survivability is a big thing. So I've never had. I'm like Ray. My house peaks out at 28 degrees. The coolest place in the house is by the leaky fireplace chimney. If you get down near the hearth, it's even lower than 28. But so that's free running mode. When Tony first did my house, I think the cooling logic is probably the reason why there's anything in that area from 28 to 30. I mean, even though it's negligible. I haven't really experienced that, but it's so little, I'm not going to argue about it. But the two red lines there are sort of passive survivability. If it's below that 12 degrees, then it becomes unhealthy long term. And then above around the 30, it's starting to be, if you're in there for a long time, it's unhealthy too. So I've just got these from somewhere, I don't know where it was, but Aysh, you're looking at me strangely. So I think they're sort of the limits of comfort, and the house is pretty much always in that band. But it does need help towards the lower end. But the thing that's interesting is that the 15 to 18, it's a pity they don't sort of break up degree by degree, so we could have a cut off somewhere. But this is inaccurate. But I can, I'm pretty comfortable at 16.5 degrees, and so is Dong Chen. We had a chat over a beer in Dubai once, and he said 16.5 degrees his trigger point for putting a heater on. And I said that's mine too, exactly. Even though he's a skinnier Chinese person and I'm a more rotund sort of Australian guy. And Sherry Ann's the same too. Her comfort's about the same. So 20 degrees is not where we have to be all the time. In my bedroom, I jump up out of bed. If it's 16 degrees when I get out of bed in the morning, it doesn't worry me. I don't need it to be 20. Nato wants it 20 at 7 o'clock. I'm gone by then anyway, but they want it to be 7. So that, I'm not that picky. And I think people in naturally ventilated, naturally conditioned buildings aren't the fussy types. They're not the dial setters. They're not they don't have a dial. So I can't put a dial
Actually, it doesn't come to energy or comfort here. The reason why the 18 to 21 is very crucial is the fact that for Sydney climate in winter, if you are operating your building at 60% humidity, then at 15 degrees, water will condense in the glass on your windows.
I've never had that.
So if you have condensation of the window, then it becomes a health problem. So if you're breathing,
absolutely.
There are, you have a house full of people, you have more children, you have more people there. It depends on what you have in the house, right? Not every house is the same. So when you have condensation, then it becomes a health problem. So it's not energy, it's not comfort. So health precedes
if the mud walls are absorbing that constant condensation, is that taken into account?
single skin mud wall, then it allows for the transpiration, it's fine. But when you have a composite construction, when you have insulated mud wall or any construction, at 16 degrees or 15 degrees in your space, you will have condensation and that creates mold. So it is not about personal comfort or, World Health Organization has come out and said you should have your internal spaces above 18 degrees to make sure that the space is comfortable. It is not about what we can bear, that comes down to the person and how much you are exposed
I mean, the clay absorbing the condensation so that it doesn't actually.
It's not the clay, it's the glass. It's your frame, window frame. So you have mold forming around the corners. You have to keep cleaning it. So there are some places where, no two houses are the same. That's why compliance in residential is so difficult because no two houses operate the same. You have exactly the same structure where you have a young family, you have exactly the same structure where you have a retired couple, but then they could be cooking quite the opposite. So we can't generalize it.
But I mean, with the clay walls, like in a bathroom with clay walls, like a friend with a bathroom, just a conventional house, always steaming up in the bathroom with condensation and the cold mirrors and things. And he lined it with clay. And the problem went away. There wasn't the moisture there to condense because it was absorbing it, or the steam when he was having his showers, so that the glass, the mirrors weren't. It just wasn't a problem anymore. And that's what I think.
Okay, well that's good. I don't have condensation.
That's good then.
We had 4 kids in the house, 2 adults, 4 kids, no condensation.
Can I just jump in for a second? It sounds like it's just because you're saying you have the windows open regularly all the time, so that's going to deal with condensation.
Yeah, it does.
So recently, but the NCC's got always changed with condensation.
Well, they've got a real problem with condensation because of sealed up insulated houses.
Yeah, exactly. It's generalising. So if you go to someone living in an apartment in the middle of the CBD and they're not open the window, they can't open apartments, so it's got mold issues. Really talking about.
Sometimes the bathroom in the middle of the house.
Exactly. So now it needs to be vented, it needs to be timed for the sewage, all these things. So it's just that it's a generalisation. That's what all these reports are trying to do. But what you're saying is it's not actually how you live in these buildings. You don't live in them. You're open cut rates open up all the time.
Yeah, look, when I started in design and building, the recommendation was for 1 to 3 air changes an hour, and that's a natural, not at 50 atmospheres. So you're going to multiply that by I forget 20. Yeah, so we're talking about 20 to 60, and you're talking about in passive house getting it down to 5, 3.
5, 6. House.
Yeah.
So there's a difference. You're talking about the ventilation, not the infiltration. The 1 to 3 air changes an hour.
Yeah.
You're talking about is the ventilation.
Oh, yeah.
So passive house is not, ventilation is very different to insulation. The building air tightness is, nobody's stopping us from opening the windows or ventilating the house or. It is about what happens through the system.
The thing that stops them opening their house is that they think they've got a perfect house and it shouldn't be open because the machine will do the work. And that's what happens with all new houses. Sorry, Kirsty.
No, you can't.
But also, what he said is, a lot of people, when they live in their house, they're getting up at 6 o'clock and they've had a shower, they close it up for security. So the point of the mold growing is because you can't ventilate it because of the human habitation and how they're living their life. I'm totally on board with what you're saying, but the reality of how people live is we're a minority in what we do, but that's not how the majority lives.
Kirsty, you've got a question, sorry, and then.
I suppose my comment would be is that Shoalhaven, you live in a lovely mild climate. The Blue Mountains is not all that much colder, but it is colder and it is more.
Oh yeah, look, I think you have to design for climate.
So my Mudbrick place, I've been in there 3 years now, I think. Woke up this morning, condensation on the inside of the windows. Now I don't open my window at night, not looking last night, it was cold. And so the problem would have been if I keep my window open, say all winter to ventilate my house, it's just going to get colder and colder and colder. I need to keep my windows closed on cold when it's cold.
I asked the guys last night if we could open all the doors on the
on our accommodation here, which is full brick. And they said it's fine, so I just left the door open because I don't like the air conditioning, and that just made the house nice for today and tonight.
Yeah, we haven't had the air conditioning on, so but I closed the window and the door and then I opened it.
And it's cold here. There was icicles on the tables this morning.
I suppose it's just sort of saying it's perhaps, and I think what we've got the comments come up, it's a complex interplay of things rather than in the line here.
Sorry.
Yeah. With the,
It goes first. So,
would also be the overall air quality.
yeah.
You got on that, you got a lot of the furniture.
Yeah, that's right.
And that's, I guess it's harder to measure that, but cold is important, but also the off-gas. What we're breathing.
Okay, I think we're moving into a panel session.
That's not actually.
I've got a question for Peter. That slide that you had previously where you've got different monitors in the room and temperature and humidity. And Earth is always, they always say, oh, it's really good for regulating indoor humidity. Have you got comparisons of like what the outside humidity?
Oh, yeah, sorry.
and what your
It
inside is?
was doing humidity and temperature.
Yeah, so how, can you speak to that? Like, how is the,
Oh, yeah.
is it generally like stable all the way, quite stable throughout the year? What's your sort of average?
It's not always, because it's open, it'll eventually rise if it's open. You know, your humidity will come up. And in recent years, when we've had more humid conditions and warmer nights, I'm considering that I might get to install ceiling fans.
Oh, yeah.
I don't have ceiling fans. No. I have one pedestal fan, and that's adequate. But that's my plan for adapting to the future is probably ceiling fans would be the first thing.
So over this last summer, you were getting quite high humidity in the house.
Well, no, it's not high humidity. It is moderated. Everything's moderated. See high growth thermal performance of walls in Australia is not modelled. Maybe your energy fielder with Energy Plus or
Yeah,
design probably does that, but NatHERS doesn't do that. So, but I think there's problems with NatHERS, or if someone wants to ask me a question, then I can.
Yeah.
Well, I think it was getting slightly humid sometimes, but totally bearable. And a fan, when it's humid, a fan works well because there's air movement with moist air. It works better than air movement with dry air. Yes. Oh, who's the moderator? You're the moderator. Well,
speak louder and clearly.
That's okay. I have a quick question for David. You were showing the wall, the tap headland. I just wonder how tall those walls are.
The ones at Newman are 6.5 metres. That was the first project, the courtyard project, that's 6.5 metres high.
And are they reinforced or anyway?
In Newman, they have one reinforcing rod every 1 metre.
Okay. And the other quick question is that you always mentioned about the concrete slab and how you tamper timbers on top of the concrete. I was wondering if you ever consider not using the concrete slab and just build the building on there. So.
Never once. You know, like you wouldn't comply, but I mean, yeah. I mean, it comes back to the point I made before. We're trying to incrementally increase the risk in a controlled fashion. Well, we're trying to increase the innovation in a way that controls the risk, right? And if we go too far, and then you know, and there are some risks that are possible to take. I mean, if we did that and there was a failure, then our PR probably wouldn't cover something like that. So, you know, these are the factors that are involved in, you know, that are kind of different when you're doing a public building and government money.
Is Newman cyclonic?
No,
Wouldn't know what you want to do, certified, just take part.
yeah.
It would just be a flat.
I was also interested in one of those projects, the one, the hybrid heritage, one. I was more interested in did orientation, because you were constrained by the corner block, did orientation play into the design in terms of, it looked like all of the north was it from the back? You just have that big eaves to cover the round dirt to make it work well?
It just works well, that building. It's just like, I think like Aysh said, the Goldie, I mean, I was just there like 2 weeks ago. And it's just like, there's some Goldilocks thing happening there. I don't think it's like, Aysh says the climate's perfect. It's certainly not. It's very hot, very cold there throughout the year. But it just, I think we, you know, Aysh obviously guided that project quite a lot because we wanted to go single skin rammed. I was adamant that that was what we were going to do because just trying to simplify the building method and get the most out of, you know, simplify. Yeah, I mean, all this layering of buildings is hugely complex for a remote building, and so we're just trying to simplify that. The rammed earth is quite deep though at Newman, isn't it? It's do you remember how deep it is?
No, this is.
No, sorry, Wilcannia. Sorry, it's like
I think 450.
450. So this comes to the question that was being asked before about the thermal lag. Like to compensate for that, we went deeper.
Yeah, there was a paper written by Xiang Dong some time ago in Adelaide, I think, or South Australia. Veronica Sabato and Terry Williamson, supervisor, and it concluded that in those inland climates with a higher diurnal fluctuation and going thicker and heavier was the best way to do things rather than put insulation in.
Yeah.
So it is a Goldilocks climate for thermal mass. Look at the telegraph station in Alice Springs, to look at the Birdsville pub, 1 metre thick walls, all the old Pizzo buildings inland, they all had a good ability to moderate that high diurnal fluctuation. Thicker and heavier the better.
And also, you know, there's a huge difference between just the daytime operating building and a 24-hour operation. The Wilcannia one is only a daytime. You know, it's from sunrise to sunset. It's an art center, it's an art gallery. It's not something that, you know, people use at night. So your perception of comfort is quite different to when you do a house. So at a residential scenario, you know, you have all your heating coming up at night, and that completely changes the balance and the humidity and everything. So it really comes down to the building type.
What if you had to use it at night?
Sorry?
What would you change?
Well, you're not living in it. I think the point is you're not living in it. You're not living in it. So it does get used at night, but you're not living in it. And so the people, you know, everyone spoke a lot about adaptability, and you're all very adaptable. But when you're designing buildings for unknown people and public, you know, they don't know they need to adapt when they arrive, and they might not arrive adaptable, and you know, it's kind of so. But I think with a building like that, I mean, people will adapt for a few hours. You know, there's some exhibition on, or there's, you know, some going on, some event. We've all been in buildings that have been perfect for that. Living in it, like aged care and housing, is very different.
Yeah, I don't think buildings need to be perfectly comfortable at all times. I think there should be no thermal shock between inside and outside. That's what I see as comfort. But a building is like a third skin. You've got your body, you've got your homeostasis that's working. You know, your goosebumps and your hair's rising and your those things, and you've got your clothing that you're wearing, and to come into a building and strip down 5 layers of clothes into an overly heated space, which I find Victorian buildings to be when I visit in winter. If they're 25, I go in there, I go, bloody hell, get all my gear off, the beanie, the gloves, the scarf, jacket, shirt, down to your undergarments almost where you're comfortable. And I just don't like that. Some people do. Some people like to
walk around in winter in their jocks and t-shirt in the house and say, look, I've conquered the world. Whatever my climate is, doesn't matter. Set the dial to 25, I got it, and I can pretend I'm living in Byron Bay. So
If it's zero outside, you don't want to walk in and have zero inside the house.
no, that's right. No, you don't. You know, but,
I think another thing is that it's like we're all individuals, we're all adapting things differently.
Yeah.
But there are some people who might be using up to the repair and stuff that aren't able to adapt as well as the rest of us. And so building obviously something like that, you need to accommodate those people who are less resilient to the environment.
For to make it navigable or understandable, the system of getting through the process from beginning to getting it signed off. There's a lot of people that no idea, and there's others at different levels, but just thinking, making a flow chart for different states or whatever, that a person could just look at and say, oh, okay, I've got to do this and this and this, and maybe this way or that way. Just to make it simple.
No, yes.
There's so many different consultants.
It is very difficult. I'll tell you, because for a single architectural design, there's about 100 different things that can make matters work. You know, like how we saw, every single thing adds or changes the result. Okay. So if you just give me the plan, don't tell me anything about the construction system. I can probably run it and give you n number of combinations of construction systems that'll make it work and which won't make it work. So the best thing to do is to engage with your sustainability consultant, energy assessor, very, very early on in the piece. And this is something we tell to a lot of residential architects. Please come to us before you've sold your client their dream. You know, don't tell them the dream and then come to us. Can you please do a Band-Aid solution? Because then it becomes too expensive for you because you have to keep changing it. And then it becomes too expensive for the client. And oftentimes we find that it goes to the bin because it's just not buildable. We see every single day, oh, I've got my design. Now I've costed it. It's just out of the roof. I can't build it anymore. It's just too late in the piece. You need to start it early.
I think he was talking more about the layman. You go to the council website, basically, they will tell you what they need for you. Is that what you're?
Yeah, but there's so many different layers of consultants.
Yeah.
I mean, you could, part of my other question was going to be, is there a one-stop shop? If you really want to be locked into one thing, but what is the process of doing?
That's usually where
That's the value of architecture.
That's the value of architecture.
That's why you need an architect. You
Yeah.
should be on the Institute of Architects board. That's why you need an architect. You need to get an architect who solved a problem similar to yours, and use that architect to help solve your problem. I mean, that's and that, because they've solved that problem before, they would interface with all the other consultants, you know, all the other. That's why people come to us for certain types of buildings, because we've
People
solved that
wouldn't
problem.
even know what was just told the audience.
But Barry, I think you're talking from an owner builder point of view.
Yes.
Maybe yes, maybe not.
Well, it's just fossicking out that information, so then you can have, say, a building designer, but yes, every state's different, and then you can, I don't know that whether nationally the building codes are the same, but it's, you know, coming back to climate, personal comfort, everything is just so variable. And years ago, probably back in whatever day, you just got a matchstick, you stuck it on and you went 6 befores or whatever, and that was, you didn't even probably need to go to councils, but that was before we had running water, you had water tanks, you know, for my grandparents, you know, that's how it was. So it's a whole different world.
Your home's not bad. Your home's not a bad research document. I don't think it's perfect, but it's got some good, and it's free online.
I was going to ask actually, what would you say? Because a lot of the things we've actually been discussing today, and to try and help a lot of the range of different people, professionals, homeowners, potential builders, that sort of thing, to try and understand some of the building science. What sort of resources could be available to people to sort of to try and get a grip on? I know Peter's referred to your home, which is a great, excellent resource. But I think trying to understand some of the building physics of people.
What we're looking for, what we've asked for, we've convinced NatHERS that they've got problems. It took 20-something years, but finally we've convinced them in 2019 that there should be a way of using the same tool to work out whether that's a good sailing boat, or that's a good motor boat, that's an efficient motor boat, or that's an effective sailing boat. And they're working on it, still still happening, but that would be using more of a free running look at the building, see how it operates, fix it up a little bit, but you're looking for how well it performs without heating or cooling in an adaptive comfort sense. And that is, I don't think it's that hard. I think if you look at passive survivability, you look at air quality, you look at climate change resilience, and it's a reasonably comfortable building, it should get a big tick. If you've got a seal up insulated box and an air conditioner, if a building needs to be air conditioned, if it doesn't need to be air conditioned, it's a sailing boat. If it needs to be air conditioned because it needs it, it can't be comfortable, then you have to look at envelope efficiency and how many litres of diesel it's going to use per nautical mile at your cruising speed, sort of like a motorboat. So this one here is, how well does it sail? Can it go into the wind? Can it go downwind? Can it go crosswind? How well does it sail? And if it can achieve that through natural ventilation, control of natural ventilation through natural conditioning, maybe give it a big tick. And this one here is
already
worst
doing
practice.
that. I guess NatHERS is already doing that. We do have window operation equations in NatHERS.
Well, they didn't have it for a long time.
No,
didn't
no,
they?
they've got the E-star temperature already. So if, say for example, 3 o'clock, 4 o'clock in the evening, you open the bedroom windows. So 4 o'clock, you have to start conditioning the bedrooms. You need a certain temperature. But if you find the outside to be very warm and pleasant, it doesn't switch on the air conditioning first. It actually opens the windows. So NatHERS does take into account the fact that we are able to use natural ventilation where and when possible, and it only closes the windows when it is not allowed. So those equations are already built into NatHERS. And if NatHERS is sort of deeming your house is not performing to a certain standard, it means it is not performing to a certain standard. Okay, it is a compliance tool, and it has got a certain band of temperature differences. We might have variations, but it's a compliance tool and it is set on a standard. So we have to comply with that. But going back to your question of what we can do, see, we've been thinking about this problem for a very, very long time. We usually work in the commercial building space. We don't do a lot of residential. We do a lot of government regulatory work in the residential space. We don't do individual consulting. But after the 7 stars, I've spoken to a lot of architects, to a lot of assessors. So architects, so what happens? How are you going to get it to 7 stars? Oh, we'll just change this basics consultant, or we'll just change the NatHERS consultant, and they'll be able to work magic. With a NatHERS consultant, they are struggling at this point because there's just so many n number of repetitions, iterations going back and forth. So what we thought was we are building on a product at this point where you bring your plans, very, very early design plans. You don't have a lot of information. You just basically know, okay, my walls are going to be ram dirt, or it's going to be double brick or brick veneer, whatever it is. You know some information about your building materials, but you have a basic plan. You're able to put it through the system, and it is able to give you an estimated NatHERS rating with a plus or minus 10% correction factor. And the plus or minus 10% is because we still don't have all the information that's required for an actual rating. But then very early on in the piece, a homeowner, the architect, and the assessor, it's a platform for all three to interact, is able to know that, okay, this building is closer to 7 stars. You're at 6.5 stars. Now, this is salvageable. The assessor can do something about it. The architect can fix it. No major, it's not a huge, it's not a bypass surgery, open heart surgery. It's a few band-aids. You'll be able to get over the line. If you're at 5.5 stars, No, there's a major redesign that's required. And then with the simulation runs, we are able to give you better results to say, okay, this is the problem room, probably this is the problem window. If you do something to it, it will improve the rating. Because NATAS, it's just maths, pretty much. Its simulation is not, it's not very difficult. It comes down to maths, what is each room doing? What is each window doing to that particular room, and where things are going wrong? We are able to pick that out. And we can get down to the surface level, and we can tell you, where exactly things are going wrong.
The problem I see with NATO is, is that the ventilation logic is very simple. It's not how I run my house. It's not how I sail my building.
I'm not saying NATAS is foolproof, but that's the system we've been given. We have to comply with NATAS. If I have to change, I'll go for something completely different. You've got more sophisticated engines, but this is what is required for us to get an OC. So we have to do it. It comes down to that.
And what Aysh is describing is how we work, right? We're starting a new project, and the first discussion we have is about building envelope. Now, we have limits. Our limits would be constrained so because we can only build in a certain way in certain locations. We showed you some of the ones that we wanted to show you, but there are other ones that we don't have a choice of the building system because of the location in the country. But the answer to the question is to do that early, to have that, just as Aysh is saying, have that conversation very, very early. We have it even before we draw a plan. We talk about building envelope before we.
I think that the problem started in 2003 with the aims and objectives of the building of the provisions. They said that you have to have a building envelope that can efficiently use heating and cooling energy. If they had made that number 3 aim, it would have been better. But the number 1 aim was to design the building so that through design, it could effectively negate or minimise the need for heating and cooling through the use of naturally occurring conditions, like the cool of night, the heat of day, solar gain, all those things. We would have had a much different way of looking at things, and passive solar design wouldn't have gone down, and silly design wouldn't have gone up. Envelope efficiency and all the following conversation.
Just examine your logic there. Sorry to jump in, but just specifically with regard to that. So when your house was looked at through Passive House, it was actually looking at how it worked, and it came up with 8.2 stars.
I don't know how it worked. But
I know that you don't, but I think, sorry, I've forgotten your name. I think that you do know how that worked, and it makes sense to me, I have to say. So you might think that it was something dodgy, but it might also
I don't think it was dodgy
physics.
necessarily.
It might be good physics.
It's just having trouble coming to terms with the likes Passive House now.
I think I love their modelling.
Passive house program, obviously, they would have, because you're really holding against the air tightness. But if it went 8.5 through passive house program, the air tightness numbers would have
No, I think I'm not sure what the modeler did. He must have put the air tightness at 0.6, otherwise it wouldn't even give you a pass. If you don't hit 0.6, it won't pass, but you can't get a result, okay? So he's assumed it at 0.6, and if air tightness being 0.6, then what is the result? So it's giving you an equivalent number, okay? But
No, he didn't assume it was that high. He assumed much lower than that. He assumed it at 3 different levels, and he said there wasn't a flow or a test. So, but it doesn't matter which level of air tightness, the results are still good.
But I'm very surprised that a passive house program is able to give a NATAS equivalent, because I do passive house modeling, I do NATAS modeling, I also do Energy Plus modeling. And the biggest problems that we've had is we can just never make it equitable. Okay, it's 3 different modelings, 3 different assumptions, and 3 different systems, literally equations altogether. So it can just never be equitable. What works in passive house will sort of, like for example, NATAS mass works so well in NATAS. Your earth coupling is just brilliant in NATAS. Mass is so very well understood in NATAS. Energy plus, yes, in big buildings, it works very well. In smaller buildings, maybe yes and maybe no, depends. It depends on the modeler who's doing it. Passive house doesn't work for mass. It doesn't, no.
We've got just a couple more questions.
Yeah.
Yeah, I was just curious, how is it that volume built houses seem to get to all these star ratings seemingly so easy when there's no real architectural orientation there, like super friendly?
Because the system was built for them.
Yeah.
Complying with the code doesn't mean you're doing anything brilliant. Complying with the code is just that you're meeting the least requirement. You know, you are just building you're building a legal building in the country. Anything below that is not legal. So it is, in a way, as Peter said, it is built for them. You know, it is the lowest cost product that will pass. And the modeling for the code is based on those lowest cost products. And RAMDER or any of these things are not low cost by any means. It is.
Those sort of builds also.
Sorry?
So the calculations just sort of prefer those sort of builds basically.
It doesn't. Again, it depends on the modeler. I don't think the calculation it will inherently bias RAMDER. It comes down to the climate. It comes down to physics. So at the end of the day, they might be, you know, cheap houses, but then they have insulation in them. It's just doing the basic work of, you know, stopping the heat transfer from happening. And that is what is required, you know, for you to.
Sometimes you walk into those houses, there's no aircon, they're like super hot or super cold.
Yeah, that comes down to how well it's installed. That's different. So what's assumed in NatHERS is very different to what's being built. There's a huge gap. So that's also it.
There is a huge gap, and that's the problem. And
reliance on.
When I was doing science years ago, you put up a theory and you test the theory before you accept it. And so NatHERS has predicted predicted how buildings will work in heating and cooling. In 2016, they did a study evaluation of 5-star back then. And the problem with it was that the buildings were good, well-rated buildings were operating better in winter in Melbourne, Adelaide and Brisbane, but in summer they were not operating as they were intended to operate. They were always using more cooling energy than they were predicting. And the more stars you get, the worse that gets. And that's a huge problem that it has not been resolved in the tool. And I'll tell you right now what the problem is. I've tried to tell Dom, tell Matt, but the cooling set points, are the problem. Where I live in the Shoalhaven, they've got this adaptive range of cooling set points, and adaptive thermal comfort doesn't really sit with seal-up insulated air-conditioned buildings. It's a concept that came about because of naturally conditioned and naturally ventilated buildings, but they're using a P&V method for the heating, and they're using a adaptive model for the cooling. So NatHERS says that where I live, the temperature will get to 25 degrees, 25.5 degrees before you'll want to put on an air conditioner where you feel hot. Then you'll put your fan on. There's a 2.5 degree leeway, and then the air conditioner will kick in at 28 degrees. That's when you'll start to accrue cooling load. Whereas I think in summer, anyone with an air conditioner is going to turn it on and set it to 20, 21, 22, whatever. But I'll set it to 22. It'll come on at 22. It's not going to come on at 28. And that's where they've got a shortfall in the difference between the predicted and the actual cooling loads. And I think that's a problem they don't want to admit. That's in the report. It said builders weren't putting insulation in properly. Owners were idiots and didn't know how to operate their houses. And there are lots of excuses. But I think it comes down to the cooling set points. And I can't understand how the builders can put the insulation in so it works in winter, but they didn't put it in so it works in summer. And I don't know how they can be dumb in summer and smart in winter. And I think the stands for the same. And they also said that the reason that the buildings may have worked properly in winter is because the modern houses had a simpler floor plan and they were better specified and they had more efficient appliances. But somehow in summer, the appliances and the form and everything fall apart. So I think there's something wrong with the set points, and that's one of our biggest problems, I think, is the set points are wrong.
But we need to head out for lunch, but maybe we've got time for 2 more questions.
Just a quick question.
Yeah, he was asking.
Or the comment. As a builder, really building a house, can't understand how people who want to live in their dream house have lost the power through these computer programs.
Got the inflexible use of numbers, you know.
And how can it possibly understand every single dream house and every single location across Australia fit through the computer programs? It's gonna how people lost the power to create their own house. I mean, they wanted to be in hot summer, be cold in winter. Why not? Why is it looking so?
Because they should have to live in a car.
That's what it'll be.
They should have to live in a car or a tent or something like that. Because they can't build a proper house.
Just
Like, because I think part of the problem is we don't have any lobbying power within the industry that can help with avoidance into the government, that not EBAA's trying and people are trying, but it's not like we've got a product that we can put on the market and sell and get a lobbying power behind it and build a ministry. So that's why we've lost that's what
Can I ask, because that was my question for Oliver about the deemed to satisfy requirements and what we can actually do to enable these things to become more acceptable for individual client. So can you just quickly explain how we went through, for example, the bushfire, that there was already a deemed to satisfy in the code?
Yeah.
What gets you there?
So an Australian standard for earth building would be the ideal solution because you have, yeah, lots and lots of work and, you heard, yeah, I never knew that. What Luigi was, not Luigi. Yeah, Luigi yesterday was talking about Australian standards being privately owned and that kind of thing. I never knew about that, but yeah, obviously it's a big, long process to get, to get an Australian standard made. There's also sometimes you can have acceptable construction manuals, so even just like a really good construction manual that you can maybe present. I'm not sure the process of this, but I'd say it's presenting it to the Australian.
We've got one that needs improving.
Yeah.
Yeah, it's a voluntary organisation, but haven't got unlimited time to do everything.
And
I'll help this if you want. So the way to get it to a point where it's deemed to satisfy specifically means you need to accept a reference manual that's accepted by the ABCB and then referenced in the NCC. So you can create an Australian standard all you want. You can potentially get a committee together. You could go copy the New Zealand one, change the terms, get it implemented by Standards Australia. Might cost you 10, 20 grand, whatever it costs. But if the ABCB doesn't accept it and reference it into the NCC, it doesn't exist. It still becomes a performance solution. Yeah. So the real question is, who do you want to talk to at the ABCB, the Australian Building Code Board? That's the first step. And then find out what does it take to get a construction manual or Australian standard referenced into the NCC. Because once it's referenced, then it becomes a deemed to satisfy solution. But if it's not referenced, I can't accept it as a certifier or a surveyor when you're issuing a building permit as a deemed to satisfy solution.
So even if you had 50,000 performance solutions that said exactly the same thing.
Yeah, so the first step to answer your actual question is to contact the Australian Building Code Board, who you can just email or call and say, I'm interested in undertaking this process, getting a construction handbook put together for rammed earth construction. What's the process? Who can talk to me and guide me through the process? And then where you take it from there, I don't know, but they're the body that undertakes this because they're the body that write the NCC. Also, separately, one thing I saw from all of this presentation, NCC 2025 has been indefinitely delayed and there's no release date in Australia for it.
Okay.
So we're expecting it in our profession to see it.
So when was this indefinite delay?
It was delayed. So we got an email at the end of February saying that the draft release had occurred and that they at this stage have definitely delayed and they have no time frame. Dutton's got no control over the process whatsoever. But the ABC there is completely independent from government, in the same way of most
Sorry?
of our, like the AEC.
2019.
But,
We did see that.
the 2020, so we'll be running on MCC 2022 for the foreseeable future. You probably won't see a 2025 implementation until either mid next year or maybe even 2027. Or they may get to the point where they just skip it and wait to 2028 to bring out the next one. So that's the current situation in the landscape. But even if that happens, in Victoria and in most other states that I'm aware of, there are allowances inside your state building acts to allow us to assess to the previous building code if the design had been created under that code. So I'm not quite sure how the changeover happened in New South Wales for like Seventh Star Energy, but in Victoria, for instance, we would have just issued the Section 10 compliance statement and said, do it to the previous code, like whatever, no one cares.
Yeah, just related to the energy efficiency stuff, I might be incorrect here, but from what I'm witnessing, hearing from the conference, a lot of the issues are arising out of the DIY passive stuff. My experience working on lots of different projects is that the energy efficiency generally goes through relatively straightforward, relatively easily, and that's through NatHERS, most of our clients, but that's also they're using an energy assessor. So I think especially like that presentation, around Earth and the Stars, like if you're going to that extent of, you know, really changing your original design to a point that you don't, you know, it's not what you wanted, I think it's definitely worthwhile engaging an energy assessor. Like this, yeah, you see the knowledge that Aysh has about this stuff, they're able to, you know, work with that software that everyone's struggling so much with, and give appropriate recommendations. And also, we don't write performance solutions for energy efficiency, but they can be written for energy efficiency. So if you can't meet that 7-star rating or whatever it is, a performance solution can be.
No, not for energy
Not in New South Wales.
Not in New South
Any state except New South Wales.
Okay.
You accept performance solutions in Victoria?
Yeah, absolutely. I do them constantly because, for instance, in Melbourne, regular construction, yeah. If you go in inner Melbourne into like Brunswick, which is probably, you know, like being in Parramatta or one of the inner suburbs, imagine that. The, you know, small blocks, constrained sites. You know, you might have major overshadowing from an apartment block next to you, so you've got no solar passive volume gain. It's literally impossible to hit 7 stars. Like, can't be done. Doesn't matter what you do to the building, you cannot hit 7 stars. At that point, we refer to a performance solution and then do like Verb or the thermal assessor will give us their actual model, like the full set of modeling, and we'll accept it based on.
Verb is understandable, but I'm talking about an actual.
No, I've done full performance
verification,
solution before, like not Verb, to give me the actual calculations. Yeah.
So we don't want to.